from some high energy state that is located somewhere here, indicated by this red ball, and then you let this red ball roll down the hill along the energy landscape. And the energy landscape is designed in such a way so that it has a bunch of local minima. And each local minimum is called a memory vector. So like here in this cartoon slide, you can see that there are 4 memory vectors that are denoted by xi1, xi2, xi3, and xi4. And although I took the liberty to project this network in a one-dimensional space, so essentially on the y-axis you see the energy, on the x-axis you see the state of the system, in principle it's a very high-dimensional system. And these patterns or memory vectors xi, they are also high-dimensional vectors, right? So essentially you start somewhere high up on the energy, then you let this state roll down the hill until it reaches the local minimum. And once it does so, you say that associative memory has retrieved that state, that fixed point of the dynamics from its parameters, right? And the reason why this idea is called memory, because you can think about this whole dynamical relaxation process as a process of memory recall. You give it a little bit of a cue what kind of pattern you want to retrieve, and then the dynamics does the rest of the job. So that's the reason why it's called a memory. Yes. Mm-hmm.
Controlled by some parameters.
Correct.
Those would be adjusted probably very somewhere.
Correct. Yes.
And the final state after you relax, that's retrieving the memory itself, and then something some environmental view made you recall that memory. Is that the initial condition of this picture? Is that how you think about it?
Yes, there's a couple of ways how you can think about this. One thing is the initial condition, and often it is enough. And in fact, in perhaps like 90% of what I'm going to discuss today, it's the initial condition that decides which local minimum you're going to end up approaching in the limit t goes to infinity. But you can also drive the system. You can imagine that there are some input currents that are provided by some kind of external stimuli, right? And those input currents, they can also bias you towards one memory versus the other. So there's a couple of possibilities, but mostly you're right. It's mostly the initial condition. And by the way, to clarify another word, associative in the title, right? The reason why it's called associative, because this whole nonlinear dynamics associates the initial state with the final state corresponding to the fixed point, right? But it can also be more like heteroassociative in some situations when you have 2 different kinds of stimuli, for example, voice and image, right? And you want to associate those 2. So like the capabilities of modern Hopfield networks, they allow for all these possible variations. And I'll discuss some of them today. Right. So that's roughly speaking the high level idea. And let me just give you an intuitive sense of what kind of problems this simple idea might be good for. And these problems are kind of, pretty standard. They go back to the 80s and everyone knows about them. So nothing new here. So imagine that I'm given a bunch of high resolution images, and I'm going to treat these images as patterns that I would like to memorize. So what I can do is I can take those images, I can encode them somehow in my associative memory network, and then I can start with the initial state that corresponds to this kind of pattern. So what is done here is I took a memory, one of those images, and I have removed 3/4 of that pattern. And I gave this state to this associative memory network as the initial state. So now if you let this red ball roll down the hill along the energy landscape, you can see that associative memory manages to reconstruct the complete pattern. So essentially, you are given some kind of cue about which memory you want your network to be biased to. And then the network does the rest of the job. So this is one standard task, and I'm going to refer to this as pattern completion task. A related but slightly different task is denoising. And that task is illustrated right here on the right. So again, I start with some pattern, and I have added a lot of Gaussian noise to it. I've added so much noise that by and large, you can't really tell what is plotted in this image. Yet, if I give it to the associative memory network, you can see that it manages to remove the noise and reconstruct a nice image of the boat, right? And perhaps even from these high-level examples, you already start seeing some parallels between these sort of ancient ideas and some of the modern stuff, like masked language model training or diffusion models. Because in some sense, what we do when we train large language models, we do precisely something of this sort. So we tokenize the text, or if we are working with images, and then we mask some of the tokens, right? And we make the language model to predict the mask token. So in some sense, you can think about this task as one token being reviewed and 3 tokens being masked. And the associative memory needs to predict what are the missing tokens. And in the diffusion model, we do something a little bit similar to what is shown on the right. So we take some pattern, we add a lot of noise to it, and then we train a neural network to remove that noise. So even at a very, very high level, you already kind of see that there might be some relationship between these ideas and like the buzzwords that we read about in New York Times these days. So, and you know, just to wrap up with this slide, I always like to stop this little animation somewhere in between, and hopefully if the resolution of the screen is good enough, you can see the shadow of the broad in the background, right? Maybe you can see it, maybe you can't. Yeah, and this sort of, you know, shadow illustrates a property that is kind of, you know, ubiquitous to these kind of networks, that they are collective systems. So it's not just, you know, it's not just a lookup table. It's not just you picked up the closest pattern and you go like straight to it. So it's a very nonlinear dynamics that explores the space of many attractors and many memories, right? And kind of, you know, in fact, like when I build this little simulation, I put like about 10 different vectors into it, and it's hard to see them, but they're all there. And in some sense, all these memories, they are trying to attract the state of the network towards them. So it's a collective computational system. So let's now try to make this idea a little bit more mathematically defined. And famously, this has been done in the 80s by John Hopfield in this paper that is mentioned here at the bottom of the slide. And what Hopfield and others realized, that it's possible to describe, to mathematically formalize this idea in the following simple, model. So imagine that we're going to describe this network by a state of binary vector sigma I. So sigma is a little bit like an Ising spin. It can take 2 values, plus or minus 1. And there are n of those variables. And essentially, it turns out that you can think mathematically about these capabilities that I described on the previous slide if you think about the following energy. So the energy is a quadratic form in terms of sigmas. And for simplicity, let's imagine that this matrix Tij, which is a symmetric matrix, is defined according to the following rule as a function of the memory vectors xi. And I want to emphasize here that these vector xi's are exactly the same vectors that I have defined on the previous slide. So essentially, the upper index of these vectors, xi, which is denoted by mu, denotes different patterns, right? So mu equals 1 corresponds to the broad, mu equals 2 corresponds to the bold, etc., etc. And there's also a lower index I that is not shown here, but it sort of indicates the projection of these memories into the vector space in which they are operating. And by the way, this projection does not have to be directly into the image plane. It can be in some latent space learned by some sophisticated neural network. So like in that regard, this is a pretty general framework. But so what is important is that there are these vectors with an additional vector index I, and you can construct this symmetric matrix Tij. And what is possible to show is that if you try to embed certain number k of such memory vectors into the system, assuming certain properties of statistics of how these vectors are generated, you can show that the maximal number of memories that you can store and retrieve from this network scales, roughly speaking, linear with the size of the network. So essentially, the largest number of memory states that you can retrieve from such a dynamical rule scales like 0.14 multiplied by n. So capital N is the size of the network here, and 0.14 is some numerical constant that comes out of some, statistical physics computation. And if you think about it, it's a little bit annoying property of these kinds of networks, because what it tells you is that there is only a very small amount of information that you can work with in a controllable way. using this old Hopfield network. So essentially, if you have a network of n neurons, the best that you can do, you can store a small fraction of those n memories. And kind of to give you a sense of that it's problematic even for simple problems in machine learning, think about MNIST. So MNIST is a simple set of black and white images that you can binarize by, say, thresholding at 0.5 intensity. And like the MNIST image is 28 by 28 pixels, right? So, so if you treat every pixel as a neuron, then n is equal to 784, and 0.14 n is, roughly speaking, equal to 100. And for example, if your task requires memorizing a lot of such images, like the simple bound tells you that there's no way that you can memorize too many of them. And in fact, MNIST images are heavily correlated. So in reality, this bound is even tighter. In reality, you can't really memorize even like 20 MNIST images because of the correlations. So all these problems raise a question, can we somehow change that? And when I say change, we don't want to change things a little bit. We're not going to go after this numerical coefficient. We're going to go after the scaling relationship. And this brings up the topic of dense associative memories or modern Hopfield networks. So let's try to modify this energy function in some smart way so that we can actually break this linear scaling relationship. So let's, again, play a little bit with this classical Hopfield network first. So let's take this expression for Tij, plug it into the expression for the energy, and slightly rearrange the sums over indices I, j, and the memory index mu. And if you do that, you can see that the energy function can be written in the following simple form. So essentially, you take the state vector sigma, you compute the dot product with each of the memories, and then you square that overlap and sum over all the memories. And that's your energy. So the only difference between dense associative memories and this classical Hopfield network is that instead of squaring it, we're going to pass it through a more aggressively growing activation function f. So that's the formula here on the right. And essentially, the only property that I will want from f is that f is a very aggressively growing function at x goes to infinity, when the argument of that function goes to infinity. And if that is the case, it turns out that it would be sufficient for singling out the contribution of the relevant pattern and suppressing the contribution of all the competing patterns. And if you do that, then you can show that, for example, if you pick the function f of x to be a power function, and let's say that it's a power function with the power n, then the scaling relationship now changes to capital N raised to the power n minus 1. And notice that if n is equal to 2, then this new Hopfield network recovers the old Hopfield network, right? So we get the linear scaling relationship. But if n is bigger than 2, we can get a much, much more rapidly growing number of memories as a function of the size of the network. Mm-hmm. I'm going to mention this. Yes, yes. It turns out that you, it turns out it depends on what you call a synapse and how you think about this. But yeah, it's a great question. Let me talk a little bit later about this, because I think it would make more sense to discuss this later. So for now, kind of, forget about any biology. Think about it as a computational system, right? You have a network of n compute elements. And the question is, how can you design an energy function so that you can pack as many memories as possible? And also, you would like not to shrink too much the sizes of the basins of attraction. And it turns out that this kind of modification allows you to accomplish both goals. So you can pack many more memories that you would think is possible given n compute units. And you also can show that you don't really shrink the sizes of the basin of attraction. They're still approximately of the order of n. And that's a nice property. So you never really it's not really a trade-off between more memories versus less associativity. It's equal amount of associativity and you have many more memories. And kind of, just to give you an intuition, you probably know about spin glass transitions in classical Hopfield networks. So essentially, all this phase space that we are gaining here, it comes from the spin glasses. So essentially, you're kind of, you're taking away the configuration space from those spin glass states and you put them around memories. And that's a good property, right? So because spin glasses, they confuse your network. Right. So essentially, by simply making the system more nonlinear, and notice, by the way, that if, for example, n is equal to 3, then this energy function would be cubic in sigmas, right? So it's no longer be quadratic in sigmas. So like in some sense, the reason why we're gaining this bigger memory storage capacity is because we are making the system much more nonlinear compared to what it used to be. Right. So and also technically you can even use even more aggressive activation functions like an exponential function, and then you can even show that you can achieve an exponential storage capacity in these networks. So the largest known memory storage capacity for these networks is equal to square root of 2 to the power n. Of course, if you have n variables and each variable can be plus or minus 1, the total amount of configuration space is 2 to the power n. So you can pack as many of square root of that huge number into that configuration space. And that, by the way, gives you an intuition that a square root of a large number is way, way, way smaller than the large number itself. So there's still plenty of space. And essentially what you have done, you have just simply taken away that space from the spin glass states and put it around basins of attraction of the memories. So in some sense, you improve the system both in terms of the number of such states and in terms of attraction properties. Okay, so yes, so let me move on. And of course, in the
classical model, what are the intuition as well? You're taking projections. By the time I take a number of projections comparable to n, they're going to overlap.
Yes.
And so I can understand why you have my stories is an independent minimum to the energy until the C's start that I'm not worried about.
Yes.
I can't quite. Before that, we would understand.
Yeah.
So is there intuition for why this debate?
Intuition for
if I have a strong enough linearity, you're telling me that I can have
right.
Probably not, but it's still quite non-one.
Yes.
Nonetheless, part.
Right. And
there's something about what I be able to understand by thinking about two vectors.
Yeah, you would. Like, think about how you would normally derive such a result, right? So you would normally, write the update rule, for example, right? And then take a look at the signal term, which is overlap of the state with the correct pattern. And if you initialize the initial state inside the correct pattern, you're trying to ask the question whether or not it will stay there or it will run somewhere else. So the overlap of the initialization would be of order n, right? And the the subleading terms, they like if, for example, if the patterns are drawn from a random distribution, the typical overlap of a given vector with the random vector would be square root of n. Right, so essentially you need a lot of square root of n's to be able to compete with n. So that's the kind of the flavor of the argument that leads to this result. And now things are much more exciting because here the overlap would be that n but raised to some power, right? So it would be much bigger number, and still the overlaps would be subleading in n. And you also need to raise them into some power. But because the power is such a function that sort of amplifies the signal the most and suppresses everything else, you would need a lot more of those subleading terms to compete with the leading one. So that's essentially the intuition. Yes, as you will see, there are very good reasons to replace this function with the softmax, and I'm going to talk about this a lot today. In fact, and that's something that people realized a couple of years ago, if you take this dense associative memory model and you literally replace the function f with the integral of the softmax, I'll explain why it should be the integral, because in fact the activation function is the derivative of this function capital F of x. Then you would get the attention mechanism in transformers. And you can show that softmax is indeed a function that belongs to this class of functions that are very rapidly picked around the memories. So in fact, for transformers and for dense associative memories with the softmax activation function, you will get all these nice properties in terms of superlinear memory storage capacity. And in fact, it turns out that it's exponential storage capacity as well. Okay, so I'm going to move on. So of course, when we do, by the way, there are some questions in the chat, and I don't know if I should. Oh, I see. I guess we fixed that one, right? So like they can hear us now. Okay, sounds good. Yes. So of course, everything that I have just described was about binary variables, right? And you can do a lot of nice mathematics with binary variables. And you can also do a lot of nice mathematics with continuous variables, but it's a little more complicated. However, when it comes to practical applications, we need to have continuous variables because in deep learning, everything needs to be continuous. We want to train systems with backpropagation. We need to differentiate all the activation functions. We're not allowed to work with binary variables normally, except for some special situations. So the good news is that all the same properties that I have just described for binary variables, they pretty much identically translate to continuous variables as well. So essentially, if you pick the activation function in the right way that is sufficiently rapidly picked around the memories, you will also have the superlinear memory storage capacity for networks with continuous variables as well. So I'm not going to talk about this right now. I might talk a little bit about this towards the end if there is time left. But for now, just please trust me that if you replace the Ising dynamics of flipping spin by a continuous time differential equation. So essentially, if V is the state of your network and you write the time derivative of that state being equal to some specially chosen nonlinear right-hand side of this differential equation, then it is possible to find the global Lyapunov function for these systems, and it is possible to prove that they're going to the fixed point, and it is possible to calculate the number of memories that such systems can store. And by and large, the conclusions that one can arrive in the binary case, they also hold for continuous systems as well. So as I already said to the answering a question here, it turns out that the system is actually extremely closely related to transformers. And as many of you know, transformers is essentially around the world these days, right? So essentially, these are the architectures behind systems like ChatGPT, Llama, BART, et cetera, et cetera. It's also, there's a lot of computational elements of transformers that are put inside models that do diffusion. So it's a very, very important architecture that kind of is state of the art pretty much in every domain right now. And essentially, I'm assuming that most of you guys have heard about transformers, but if not, a transformer is nothing just a feed-forward neural network that has this structure. So this is what is shown here is one transformer block. And the whole transformer is composed of many such blocks stacked on top of each other. So essentially, inside each of these blocks, you have two important operations. The first operation is the multi-head attention operation. And the second operation is a feed-forward network. And in addition to that, you have a couple of skip connections and layer normalization steps. But essentially, that's a feed-forward neural network that is kind of, designed in a very smart way for doing what it is supposed to do. And it turns out that the most important element of this transformer block is this multi-head attention operation. And this multi-head attention operation, essentially, it routes the information between different tokens that are presented to the network. So it turns out that if you take the dense associative memory, pretty much in this form that I have described on this slide, and you replace this function f with the integral of a softmax. And a softmax is just a fancy word for a Boltzmann distribution, by the way, right? For those of you who don't know. So if you replace this activation function with the integral of the softmax, which is log of the sum of the exponents, then this model identically turns into the self-attention mechanism in transformers. And the reason why this is important, it is important for two reasons. First of all, transformers are by and large empirical systems, and there are like, thousands of people around the world that are playing with them empirically, but it's very hard to understand what they are doing computationally. And there is certainly almost no theory about transformers. On the other hand, there is a fair amount of theory about Hopfield networks and dense associative memories. And for that reason, it makes sense to think about computational properties of transformers through the lens of dense associative memories, through the notions of basins of attraction, memories, et cetera, et cetera. That's one reason why it's sort of fruitful to have this theoretical correspondence between these two classes of models. Even more to that, if we really seriously take this idea that large language models, transformers, are just very complicated and carefully designed models of associative memory, we can even push this agenda a little bit further, and we can start with associative memories, and we can try to design better transformers. And essentially, for the rest of my talk, I'm going to try to tell you about our efforts of doing just that. So we're going to try to leverage these theoretical insights about dense associative memories, about basins of attraction, number of patterns that we can store in those memories for designing better kinds of transformers. So let me introduce you this architecture that we have called the energy transformer. And the energy transformer is going to be a very carefully designed model of dense associative memory. So essentially, it's a little bit like transformer in the sense that there is something that is called an energy transformer block that is applied to the inputs. And in contrast to conventional transformers, which are feed-forward neural network, energy transformer is a recurrent network. So essentially, you take the input, you apply to it the energy transformer block, and then you take the output and you send it back to the input. So it's going to be a dynamical system. And with some update rule that is shown here in the discretized form, or you can write a differential equation if you wish. And we would like to design the energy function in a way so that it's as similar to the conventional transformer as possible. And it turns out that under a couple of assumptions, you can do that. So essentially, for the purposes of my illustrations, I'm not going to work with a language because it's a little bit harder to look into language because it's hard to visualize it. I'm going to work with images. But, transformers are agnostic about the data domain. You can work with images, you can work with time series, language, it doesn't really matter. So let's think about images. And here, the setting is pretty much very similar to the standard setting of what is called VIT, which stands for vision transformers. So you take an image, like the one that is shown here. First, you patchify that image, which means that you split it into non-overlapping patches. Like here, I have split it into 4 patches. And then you encode the pixel-wise content of each patch into some latent space by, say, multiplying by matrix, maybe applying some nonlinearity. So then you give this state to the as the initial state to this energy transformer. And before you do this, you mask some of those patches. So here you can see that 2 of the 4 patches are masked. That's why they're gray. So then you do one more step. What you do is you add positional embeddings to every patch. And that's going to be just some kind of learnable vector that would indicate where the patch is inside the image plane. And in our setting, those vectors will be learnable for backpropagation. So essentially, like we just initialize them with some random variables, and then we see what kind of positional embeddings this network needs to learn. So then you start with this initial state that corresponds to the sum of the 2 things, and then you give it to the energy transformer. And what the energy transformer does, it descends this energy. So here on the x-axis, you see time during this temporal evolution, and on the y-axis, you see energy. And ideally, we would like the energy transformer to figure out a plausible autocompletion of those mask tokens. So again, it's a little bit like what we do in large language models, right? When we mask a couple of words in the systems like BERT, for example, and we run BERT and we want a BERT to predict what these mask tokens are. In a very similar way, here we predict what the missing patches, what the mask patches are. And I want to emphasize here that unlike the illustration that I have given on the first slide, where I have known upfront what the memories or pattern should be, because you gave me like 10 images and I just literally put them by hands into the Hopfield network by using some Hebbian learning rule or just literally embedding those. In the energy transformer business, that is not allowed. right? So essentially, it should meaningfully operate on any kind of reasonable image. So for example, if I have a pre-trained transformer, I can take the picture of this room, which never appeared in the training set, and I should expect that the energy transformer meaningfully reconstructs the missing patches. So in some sense, it shouldn't memorize specific images, it should memorize the rules about how images are constructed. The kind of rules that if you see a left portion of the face, they got to be a right portion of the face, and they should be properly located, be of the right size, etc., etc. So, yes, question, no? Okay.
The efficient symbol does that denote happening additional information with the
yeah, it's a very good question. You mean like this positional embeddings, right? Yeah, you know, it's it's really like a weird thing. Like in physics, the first thing that we learned that you're not allowed to add apples and oranges together, right? But in machine learning, people often do, and that's an example of such a thing. Indeed, like positional embeddings, they have nothing to do with the latent embeddings of the patches, right? And you know, normally you would expect it; it's natural to keep them separate. But in reality, people just add them together, and backprop figures out that, you know, they are measured in different units. You know, it learns that those units needs to be adjusted. So in practice, people just add them together. But you can concatenate. You can sometimes people also put some kind of, you know, predefined grid. For example, like sinusoidal waves, right? So like it's not just like you can, for example, take this vector and dedicate the element number 1 to be a coordinate along a sinusoid with a certain period, and coordinate number 2 to be a sinusoid with a smaller period. And you can kind of, you know, encode the position in the image plane through those Fourier harmonics. So there are all kinds of strategies, but, you know, simple addition works quite well. Yeah.
You're saying
That's fine. Yes, maybe it is factorized because, you know, all these systems, they have a lot of parameters, right? So you multiply them by some high-dimensional matrices, and probably the matrix that that this state is being multiplied by kind of learns that there is some portion of that matrix probably stored in some subspace of that matrix that is responsible for position, and the rest of the matrix is responsible for content. So indeed, it's kind of, you know, you could have provided that information up front, but for some reasons that I personally don't understand and nobody else does, just addition works the best. Maybe because gradients are propagating smoothly while you're training through backprop for some kind of bizarre reason that we don't know. But that's like what most sort of state-of-the-art models do. They just add things together and then let backprop figure out who is who. Excuse me? Mm-hmm. Yeah. Yeah, no, it is extreme. Yeah, completely agreed. In fact, it is extremely important here, right? And I'll show you what these positional embeddings look like if you want later on. So like if they were random, the network would not work at all because I haven't described the energy transformer block, but similarly to the conventional transformer block, it's completely agnostic about location of the tokens. So it's permutation invariant about how you put. Yes, it needs to have that information. Otherwise, you have no idea if this patch is located here or right there. Yeah. So it's extremely important, but kind of, you know, relating to that question, it's slightly unnatural to just add it, but in practice it works. Oh, sure. Right. So for those on Zoom, the question is, what if the training set is biased in some way? For example, it has a lot of pandas on the left. Would it sort of, you know, in the reconstruction also imagine more pandas on the left? And the question is probably yes. Probably yes. Yes. I mean, there's nothing here that would prevent this system from being, you know, as biased as any other feed-forward neural network, right? I mean, if the data set has a bias, it's quite likely going to be inherited by the model at the very least. And sometimes people have shown that models, like models with a lot of parameters, they even amplify bias. So if you have a lot of pandas on the left, when you try to reconstruct those images, it's likely that will be even more pandas on the left. So
there's kind of one between actually the prioritization process of the one transformer block versus just stacking several standard transformer blocks on top of each other and then running things through that.
Right. So the question is there any difference between recurrent minimization of one transformer block, as I'm about to describe, versus stacking many transformer blocks on top of each other? So there are many differences. So one difference is that like this energy transformer block shares the weights, right? So technically, you could have taken one block and stacked it on top of each other with the same weights. And that would be closer to this system than the conventional transformer. And in fact, there are such systems. They're called Albert, which stands for A-light bird. But even when you do that, if you take the conventional transformer block, it would not describe a gradient descent on a function. Because as you probably know, not every vector can be represented as a gradient of something, right? And that's precisely the mathematical reason why it would not be a gradient descent on some, properly chosen energy landscape. So what is cool about energy transformers is that we have designed them that way. So that essentially there is an energy. Energy is fundamental. It's the core concept. And then the equation, the nonlinear dynamics, it follows from the equation. So it's guaranteed to be a gradient. And that condition is normally not satisfied by conventional transformer blocks if you would just write them down. Okay.
And so I'm going to relate to the energy transformer and standard
Right. I'm going to repeat. So the question is whether or not there is a relationship between LSTM, which is like the most, or any RNN and energy transformer. And so the answer is yes, of course. Like energy transformer is recurrent, right? Any RNN is recurrent. So in that sense, there is a relationship. But what is new here is that this energy transformer is not LSTM and it's not any other known recurrent neural network. Because the update rule, it's not LSTM and it's not any other known RNN. Yeah, but it's a very different network, right? LSTM is a very specific network, which has like very specific set of equations. It does not have attention, for example. Yeah. Right. Yeah. Yes, the differences are completely fundamental here because gated RNNs do not have attention, right? So this network does. So like it's a very different. So essentially, like think about this update rule, right? This is the update rule that dictates how you go from the state at the moment of time t to the next moment of time. And this is some nonlinear equation, and you can obviously imagine many different kinds of nonlinear equations. So LSTM is one set of equations, gated recurrent units is another set of equations, energy transformer is a third set of equations. They're completely different equations with completely different properties, right? But they're all recurrent. In that sense, there is a relationship. Yes, I'm going to come to that in a second. But kind of, even at a high level, think about it like this. LSTMs do not converge to fixed points, right? They can just run forever. They do all kinds of crazy things. This system has to converge because it has an energy. It is bounded from below. Energy is a Lyapunov function. It is guaranteed to always go to a fixed point. So even like from a high level, this system has like very different kind of flavor from LSTM. But kind of, to give you a little bit of historical remark, a person who invented LSTM, Sepp Hochreiter and Schmidt-Huber, in fact, the contribution that I mentioned earlier, that realization that dense associative memories reduce to self-attention if you replace the function f with the softmax was done precisely by Sepp Hochreiter. You can probably introduce attention in some form. Fine. But hopefully you would agree with me that none of those networks converge to fixed point generically. Yes. Yes. Maybe you can constrain them to in some sense by putting some constraints to converge them to the fixed point. What I'm saying that the energy transformer always does. There is no way that you can do anything to it that it will not. So in that sense, at least they're not mathematically equivalent. There could be some limits where they do something similar, but mathematically they're very different.
If I take a transformer block, which is, after all, some people, in general, the vector that comes out of that is not gradient fixed.
Exactly, yes.
And so in some way, you add in the original model, but done something interesting.
Yeah.
Reduce the set of things you're allowed to do.
Exactly, yes.
And yet somehow.
Yes. Everything turns out all right and even better because, you know, transformers, again, like sort of follow up on your question, right? Transformers, like fundamentally think about the computation that is happening here, right? You start from some hint and then you want the answer. So even like that statement that you start somewhere and then you want to flow to the answer sort of already implies that the answer, it would be nice to return the answer in the form of a fixed point, right? So it's a quite desirable property to have. And that's essentially like the main desideratum here. So we try to engineer the system so that it always converges to the fixed point. And that fixed point is stable. So once you converge, you never really run away from it. It's just the answer that you can read out from the network. So that's what we're trying to accomplish here. Okay, so let me move on. So what's inside the energy transformer block? And again, you know, take a look at this picture. That's the standard one, right? That's a standard feed-forward transformer, and this is the energy transformer. So as I've already said several times, we want to think about the energy transformer as this dynamical flow system. So essentially, X is a set of tokens. The set is denoted by this index A. So A runs from 1 to number of patches in the image, or 1 to the number of words in a given context window if we're talking about large language models. And index I is the vector index of the token. So we have some time derivative on the left, and we have some derivative of the energy with respect to some variable G that is related to the variable X on the right. So it turns out that the variable G is a nonlinearity. Think about it as an activation function that is being applied to X. And this activation function can be quite complicated. If we are talking about models, typical for computational neuroscience, G could be a sigmoid of X, for example. If we're talking more about AI systems, G would be something like attention operation or layer normalization, those kinds of things, right? But the cool thing is that if the function G is monotonic in some sense, because it's a little subtle to define mathematically what it means to be monotonic for a function like a softmax or layer normalization, but at least for sigmoid there is no ambiguity, right? So if the function G is monotonic, then you can show that essentially this kind of dynamical equation always guaranteed to reduce the energy. And then the question becomes, how do we write something here? How do we design this energy function so that in the right-hand side of this equation, we reproduce something that resembles the conventional feed-forward transformer? And that's what I'm going to describe next, right? So essentially, inside the energy transformer blocks, there will be several modules. The first module is this red guy. I'm going to call it multi-head energy attention. And this multi-head energy attention would be very similar to this multi-head attention in the conventional transformer. There will also be a module that I'm going to call a Hopfield network. And this kind of Hopfield network would be pretty much a standard Hopfield network from 1984, which is like continuous Hopfield network, but it will be a classical Hopfield network. So the dense associative memory is going to be inside this red block. But this guy is going to be like the classical Hopfield network from the 80s. And the analog in the on the left-hand side of this Hopfield network would be this feed-forward network. So for those of you, by the way, how many of people in the audience work with transformers like on a day-to-day basis, just so that yeah, okay. So maybe I should just explain a little bit about this diagram on the left. Yeah, let's actually start with the feed-forward network. So feed-forward network typically is the following thing. You take a token, let's say the token is d-dimensional. You take the token and you multiply it by some matrix, and typically that matrix have an expansive properties. So you map a d-dimensional space into 4 times d or something like this. So it's a matrix that kind of expands representation. And then you have another matrix, let's call it W2, that does contraction. So essentially it goes from 4 times d back to the d. Right, that's typically what this feed-forward network is doing. So as you can imagine, this operation that I have just described cannot be represented as a gradient of a scalar quantity. But it turns out that it can if you impose some constraints on W1 and W2. So for example, if W2 is a transpose of W1, then it can be. And that's essentially the difference between this blue block, the Hopfield network, and this blue block, which is feed-forward network in the conventional language. So in some sense, you need to share the weights in the expansion of the feed-forward network and contraction pathways. So that's what converts feed-forward network to energy-based Hopfield. So this guy, the multi-head energy attention. First of all, let's talk about the multi-head attention. So what does multi-head attention do? Think about it like this. Imagine that I am this guy. I am this token, like this mask token right there. And I want to figure out whom should I become, right, at the fixed point. Because I just, I'm mask. I'm just given like some initial state that is completely uninformative about my final state. That information about whom this mask token should become comes from other tokens that are open, that are revealed to this neural network. Right? And essentially the attention operation, it routes the information from those open tokens to the mask tokens. In the same kind of way, if you think about language, right? If you train in systems like broad, you have a sentence and you mask the word in the middle, and you're trying to figure out what the right completion for that mask word is, you need to look at the neighboring words. And the attention operation, it's the thing that sort of routes the information from tokens nearby into the mask tokens and tell the token whom it should become. So essentially, that's what this thing is. And by the way, this feed-forward network, it operates on a token by token basis. So it doesn't really talk between different tokens at all. So essentially, it takes the vector and then it applies some fixed operation to that specific vector. It does not aggregate information from nearby tokens. So in some sense, like these two parts of the transformer block, they do very, very different things. And in a very similar way, we are going to try to engineer a smart sort of energy-based definition of those modules in the network on the right. So let me actually, before I go to the next slide, let me point out a couple of interesting things. So in the conventional transformer block, the attention operation and the feed-forward operation, they are plugged in a consecutive way. In the energy transformer block, they are plugged in parallel, right? So they operate on the same set of tokens, and essentially, like the tokens come in here, we normalize them in some way, and then there is attention, and then there is Hopfield, and then we add those contributions together. So that's like first difference. And the second difference is that we need to impose certain constraints on the weights of this neural network to be able to represent the dynamics as a gradient descent of some function. So how do we do this? So the it would be more or less the same. Yes, and in fact, as you will see, that's more or less what it looks, what it learns. I mean, there are some subtleties to that because you see, like in some sense, like this kind of Hopfield network is not dense associative memory. It's the classical Hopfield network, and there are some good reasons why it should be done that way. But the thing with the classical Hopfield network, you sometimes do not converge to the memory. Right, you sometimes convert to a spin glass state. And because this whole network is trained in an end-to-end way using backprop, you don't really know who is the memory and who is the spin glass state. But in some sense, that's what it does. It learns certain features, and I'll show you what these features are in a moment. And it matches them. Yeah. Yes, in some sense. But what you put inside that external memory is carefully modified from the image. So it's not just like the image itself, right? It's some kind of sophisticated way of storing the information about the image inside those memory slots. But yeah, you're right. Indeed, it's just kind of it's the same computation that I have described on the first slide. Okay, so so how do we engineer those energy functions? And so let me just show you these formulas, and I'll try to give a little bit of intuition of what they mean. But kind of don't be too upset if you don't kind of follow every mathematical detail of it. So essentially, the energy is the sum of two terms: the energy of this red block, energy attention, and energy of the Hopfield network. So let's start with the Hopfield network. So the Hopfield network is this thing. And hopefully you can immediately see the parallels between this formula and the formula that I have shown on the first slide, right? So essentially, G is a little bit like capital F. Xi is the same Xi as what I had on the previous slide, and G is the state. Right, it's the same kind of thing. And if G is a quadratic function, we get the classical Hopfield network. If G is a power or exponent or a softmax, we get dense associative memory. So there's nothing new here. And notice that the sum over memories, which are like in some sense memory slots, according to your question, right? And the sum over tokens that are indicated here by the capital letter B, it's like external, it's additive. So the energies are simply additive and independent of each token. There are no really interactions between the tokens. And that's sort of the most important thing about that part of this network. Attention operation, on the other hand, is very different. So indeed, it has the structure of log of the sum of the exponents, right? And the notations here are such that capital letters B, C, they denote tokens. H denotes heads of attention, because there could be several modules that do attention, and empirically it turns out to be beneficial to have several of those. And then essentially, if you act by derivative on log of the sum of the exponents, you get something like a Boltzmann distribution or a softmax, right? And that's the reason why this energy is chosen that way. Now, similarly to how we do conventional transformers, we have the set of queries and the set of keys. And they kind of enter this equation multiplicatively here, and there is a coefficient beta which stands for inverse temperature in the Boltzmann distribution, or in transformer world it's typically one of the square root of the number of dimensions in the attention operation that kind of regulates how sharp the softmax is. So if beta is very big, then you are focused on one set of best matching tokens, right? And if beta is equal to 0, then essentially it's a flat distribution. So that's the energy attention. And then both keys and queries depend on the input tokens, right? So essentially, if you differentiate that thing with respect to G, which is the activation function acting on X, you end up having some kind of very complicated nonlinear rule that has softmax in it, that has like key values, queries, etc., and it has a feed-forward network that comes from this term. So kind of it will look a little bit like a conventional transformer, but of course it will not be a conventional transformer. And let me just emphasize again in what places it will not be. So first of all, inside this block, the matrices will be shared, right? So it would not be like two separate matrices, it will be only one matrix. And also inside this block, notice that nowhere in this formula I have values, right? I only have queries and keys. And the matrix of values will be computed out of queries and keys, which is, some kind of restriction, but it's not something like completely crazy. And in fact, there are variations of conventional feed-forward transformers that do not have separate matrix of values as well, right? Okay, so I can see, please. Xi mu's are learned. So like what we do is the following: we initialize them with random variables drawn from a Gaussian distribution, and then we present to this network something that looks like this, right? So essentially you have some open patches and you have some closed patches, and then you run this dynamical equation until it reaches a fixed point. So essentially you run it for say 20 steps, right? And then after those 20 steps, you take out the output, the final state, and you project it back into the image plane. And you get hopefully something that looks like this. And then you take that output, you compare it with the target output, with the ground truth image. You compute the mean squared error, you get some loss function that depends on the parameters, and you backpropagate and you learn those xi's. And also you learn a bunch of other parameters hidden inside these matrices K and Q. Right, so there are in fact many ways where this network has a lot of parameters. It has parameters inside this matrix Xi. It has parameters inside WK and WQ. It also has parameters in layer normalization, pretty much like the standard transformer business. So all those parameters are learned in a self-supervised way through backpropagation. I have not. I'm sorry. Yes, I should have. But essentially, it's a linear multiplication. So you take the token X, you pass them through the activation function G, and you multiply it by a matrix WK or WQ, and that's your K and Q. So it does depend on X in some nonlinear way, and it does depend on some set of learnable parameters W. The index alpha is what is called an internal dimension of the attention. So like it's some auxiliary kind of index. Exactly. Yes. Except it's not symmetric. Yes. 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 It's a very wise comment. Indeed, it's a very. In fact, there is no really reason to have separate WQ and WK except for appealing to like machine learning audience, because they often do. Because in fact, they always appear as a product. And we could have called this matrix T, right, and learned just that matrix. Yes, correct. Yes, actually, could be low, could be high. That's yes. Controlling the rank would be the number of indices alpha. You're 100% correct. And indeed, the only thing that distinguishes this formula from the Hopfield network that we all love is that there are all these nonlinearities on top, exponents and logarithms. But by and large, it has the structure G, which is a function of X, multiplied by some matrix T multiplied by G transposed. Right? Uh-huh. Right. So the question from the chat, is there any guarantee on how many iterations do we need to arrive at the fixed point? And the answer is no. I'm not aware of any theory that we can build. Probably we can, but I don't know how to build such a theory. So in practice, we do this empirically. So you look at this, you kind of plot the energy, you see that it's kind of at some point it plateaus. You don't want to go like, you don't want to spend too much time because the thing will be compute inefficient. So it's always approximately the fixed point. It's never really like a true fixed point, but you can get close enough and you can backprop from it. And, sometimes it works, sometimes it doesn't. Yes. Mm-hmm. Correct. Exactly. Yes, it does whatever it does. Correct. Yes. 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 Yes, in some sense it does. So let me repeat the question and then I'm going to answer it. So the question is, it seems that we're having two kinds of gradient descent and two kinds of loss function. The first loss function is the energy that I'm talking about a lot today, right? And that is a function of the state of the neural network. And we are optimizing, minimizing that function in the forward pass. And then there is another loss function, which is the conventional loss function that everyone else is using, which is not a function of state, but rather a function of variables, of parameters. And we are optimizing or minimizing that function as a function of those parameters in the training path. So, and that's essentially, so that was the question, in some sense, the answer. Yes, in this framework, there are two separate functions. They have nothing to do with each other. Indeed, like the forward pass is unconventional thing, because normally it is not a gradient on anything, right? It's just like a combination of feed-forward layers. And in our case, it is. But the other loss function is always there. And the second part of the question is because the forward pass has to share the weights in order to optimize the energy, wouldn't it lead to some kind of decrease of representational capacity or computational properties of this kind of network? And the question is, the answer is yes, it might. It might. I will show you examples of tasks where it does not, it not only it prevents the network from working efficiently, it actually like, I'll show you some results and I will let you be the judge to what extent it works. Correct. Yes. 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 No, it's not. It's not. In fact, you can see that, like, let's say, I'll give you a very concrete answer. Let's take a system like BERT, like classical BERT. BERT has 12 layers, right? So you take, conventional transformer block and you unfold it for 12 layers with unshared weights. So the systems that I'm going to show you today also have 12 updates, but through the same set of weights. 12 steps only. And that's, yes, and then we stop. And then sometimes it converges to the fixed point, sometimes not so much. And, there is a little bit of numerical error there, right? But we still can train it and it works, right? So first of all, it doesn't, right? Like from my perspective, there are sort of two motivations, right? The motivation number one is theoretical, because once we have this notion of the energy, we can suddenly think about, energy landscape as opposed to some arbitrary feed-forward computation, and that can be informative. You can think about basins of attraction, you can think about fixed points, etc., etc. This immediately brings up all these theoretical notions that we do not have in conventional language. So for me, that's like the primary motivation. But perhaps you are asking about more like practical engineering application. Why would people care, right? And let me give you one example why people do care. The cool thing about these networks is that they're much more memory efficient because the weights are shared. And not only through layers, but also inside the energy transformer block. Like these models are tiny. Like the vision transformer that I'm going to show you on the next slide has like about 2 million parameters. And as you will see, it meaningfully auto-completes, realistic images. That's like tiny compared to anything that's out there, in the AI space. And there is a huge interest of using tiny models on devices, various kinds of edge devices, Internet of Things, etc., etc. Like in those applications, the memory footprint of the model is a very, very costly and relevant parameter. So in some sense, there are practical, questions around this, but there are also theoretical. I'm a theorist, so I mostly care about theoretical questions, but in some sense, these models can also be quite practical. Mm-hmm. Yes, yes. So again, so the question is about the beta parameter right there. And the question is, should it be fixed? Should it be tuned? Should it be, what should we do with this? Yes, there are three strategies, as always in machine learning. Number one, fix. Number two, treat it as a hyperparameter. Number three, learn it for gradient descent. In practice, we've discovered that learning it for gradient descent does not really work. It becomes unstable and things fall apart. Having it fixed up front, we don't really see any theoretical rationale for how to fix it. So we treat it as a hyperparameter, option number 2.
If I see something where an energy is the log of some exponential,
Mm-hmm.
I imagine that at least it's right, has something variable thing.
Yeah. Yes.
That is so awesome.
Yes. Yes. Very much useful in the subject that was separate in our talk. And in fact, no, but let me sort of give you a preview, so to speak, and maybe I will get there today. So in fact, when we introduced these models in 2016, like machine learning community was sort of fine with them. They said, okay, interesting indeed, like dense associative memories have a lot of memory storage capacity, useful computational model. Neuroscientists hated it. And the reason why neuroscientists hated it, because they said, oh, like, what you guys are saying is complete nonsense. Because normally, when we look at this matrix Tij here, right, we think about that matrix as a synaptic connections between two neurons in the Hopfield network, right? Now, imagine that we write there a power 3, for example, right? If I write a power 3 here and I take integrate out this sum over mu, I will end up having a tensor with 3 indices, right? And 3 indices, like it's like a 3 neurons that come together in a synapse. Probably you can imagine this, and there are valid biophysical systems where you can imagine such a thing. Or like 4 synapses or 5 synapses, right? If you keep increasing that, but suddenly, like this tensor T loses its biophysical interpretation. And what neuroscientists told us is that maybe the system has some computational value, but biologically it's complete nonsense, because neurons interact with each other in pairs. And it turns out that it's not quite complete nonsense. It turns out that if you introduce auxiliary neurons, you can make all the synapses in this system pairwise. And then once you integrate them out, you get this thing as an effective theory. And the same applies to the other formula that you've pointed out before.
Just follow up on that. These bounds on N, though, these would be non-effective neurons, not N physical neurons. So you kind of get back to your original.
So it requires a little bit more. It requires a little bit more discussions, and indeed, so it is important to distinguish these kind of neurons from the overall number of neurons. So, like, if you introduce those auxiliary variables, then the capacity would be still this fancy capacity as a function of feature neurons. It will be exactly the same number of those neurons, but the number of hidden neurons would be much bigger. But there are also ways around. You can integrate it out in a slightly different way, where the network would still be superlinear in the number of compute units. But that's again, it's a subject of a whole separate talk. So let me just not go there for now. Yes. Okay. So let me kind of move on. So let's say that we take this energy transformer, we train it, right? So does it work or not? So I'm going to show you a couple of illustrations of what it actually is capable of. So let me first explain how to read those images. So in the first column here, you can see the initial state that we give to the energy transformer. In the last column, in the third column, you can see the ground truth image. And in the middle column, you would see the intermediate steps. And I'm going to play this movie for you now. And essentially, as the movie progresses, time runs forward, and you will see how this state, the latent state, being mapped back into the image plane evolves in time. So yes, and you can probably figure out that the movie is looping, right? So once it gets to the end, it jumps back to the beginning, and you can probably figure out when this happens. So as you can see, indeed, this network works quite decently, right? And all the weights are shared, as you pointed out, right? But still, these are quite non-trivial images. And I should also emphasize that these are not images from the training set. So these are novel images that the network has never seen during training, right? So there was no way that the network would memorize them in some trivial way. And let's take a look at them a little bit. So let's for example, focus on this one, right? So the ground truth image here is this regular pattern of bricks. And let's take a look at the reconstruction at this image that the energy transformer is returning. Let's focus on this portion. And hopefully you can see like a very long brick here, right? That does not appear on the right. So it's a different image from the ground truth. And the reason why it reconstructs this very long brick is because the whole boundary between those bricks was occluded. So it has no clue that, that there was a boundary there. And, you could say that this is a mistake, but also you could imagine a reasonable picture that looks like the one that is shown here, right? It's, it's not the ground truth, but it's a very reasonable auto-completion of the pattern that the energy transformer sees. So another kind of interesting example is right here. So if you focus on this portion of the ground truth image, you can see two peppers. And the gap between the two peppers is entirely occluded in the initial state. And despite that, you can see that because there is this little this little stick that sort of sticks out, the model realizes that it's not just one blob of green color. There's actually like two separate, entities there, and it reasonably reconstructs the gap between them. So in some sense, indeed, this model did learn some meaningful set of rules about how natural images are constructed. And again, we can't really know for sure what those rules are. Presumably, if you see a straight line, the straight line tends to continue through the space, right? If you see one straight line and another straight line, it's likely going to be a corner. So those kinds of things. And those patterns are stored inside dense associative memory. And what is stored inside the classical Hopfield network are kind of, notions about what each patch looks like. And I'll support this claim empirically in a second.
Parameters in this particular model?
It's about 2 million. So it's a tiny, tiny model.
How large is the training setup?
It's standard ImageNet 1K. Yeah. So 1 million images or 1.4 million images. Sorry? Query and key dimension. I think it's 768 or something like this. Yeah. And I think there are 12 heads of attention. Yeah. If you, correct. Yes, the output. So once the model is trained, right, once you remove stochastic gradient descent of training the loss function, everything is deterministic. You start with the same state, you get to the same output. You could imagine adding some kind of Langevin noise. That's totally allowed. And in fact, in some applications, we have found that it's quite beneficial to add a little bit of Langevin noise to make it a little bit stochastic. We don't really fully understand why, but there are these variations. So technically, it does not have to be deterministic, but in many situations it is. Although in some it is not. Okay. Yeah. So right. So I think it's a little bit more complicated than that for the following reason, because when we train these systems, right, we generate the mask at random. So you have the same image, every time it appears in the mini batch, right, you choose a different mask. So in some sense, it's always it never really sees exactly the same training example twice. And in fact, it kind of learns to look at that example from various angles. So the question is whether or not, if there are several different images, do they correspond to separate local minima or not? I don't really know the answer to that question. The intuition that I have is the following, that the two contributions. So let me see what's going on here. So please ask the question one more time. So, yeah. Yes. Okay. Okay, fine. Ah, I see. I see what you mean.
Is there anything that their property of the landscape?
Yeah. I mean, okay, I understand. You're saying that let's make life for our network very complicated, right? So let's kind of, always start with the same mask, but have many different, final answers, right? It would probably, if you train it that way in such a difficult task as you described, it's quite likely that we'll be confused on that image, and it would probably generate some kind of blurred version of all of them. But again, we try to not to do that, right? We try to generate different maskings and sort of try to put those images into different basins of attraction in some sense. Yeah. And again, sort of, I already probably emphasized it a couple of times, but I view this block, this kind of energy, as the place where rules are stored, right? Rules about like what the natural image is. And I view this place, the classical Hopfield network, as the place where the information about what patches look like is stored, right? So in some sense, there are two contributions in the energy function right here, and sometimes they compete, sometimes they cooperate, right? So it's like a very sort of sophisticated energy landscape that's very hard to visualize, but that's the intuition that I have. So let me sort of try to support that intuition. I'm very glad that this slide comes out next. So essentially, let's take a look at what kind of internal representations this system learns. And let me also emphasize something that is very specific to this system as opposed to any other vision transformer or any other transformer in general. This system is much more interpretable for the following reason. Because essentially, every time you see a vector index, this index I, that corresponds to the token dimension, you can take whatever variable has that index, you can multiply it by the decoder matrix, and you can map that thing directly into the image plane. And the reason why this is cool is because you can pretty much ask what each variable means inside this transformer, and you can view it. You can literally look at it with your eyes in the image plane. And it's impossible to do it in the conventional transformer or vision transformer or anything because of all these layers, right? So it's not like you are operating in the same state space all the time, unlike the energy transformer. And what we thought is, wouldn't it be cool to actually take advantage of that capability of energy transformers and try to understand what different modules inside this energy transformer are doing? And perhaps inside feed-forward transformers, similar modules might be doing something similar. Maybe not, maybe yes. Over there, it's a hypothesis, but here we can see it. So let's take a look at the learnable parameters first. So remember, I have introduced these positional biases. And let's first of all take a look at them. So this is a pretty much standard way of looking at positional biases. So the right way to view them is as follows. So essentially, think about this plane as an image plane, right? So this is kind of, this corner is located in the bottom left corner of the image. So you take the positional vector, the learned positional vector corresponding to that token, and you take the cosine similarity of that positional vector with every other positional vector in the image plane. And if you do that, you get this little square, right? So and then you repeat it from another token, and kind of you do this for every token. And essentially, yellow color corresponds to maximal correlation, blue color corresponds to anti-correlation, green color corresponds to no correlation. So first of all, you do see one well-pronounced blob of the yellow color, which is a little bit like convolutional structure, right? That's like the bias that we could have put up front into the network, that the patches that are located close to each other are actually most informative for the masked patch. But the network learns it, so we don't have to put it up front, and it just kind of it appears. And so that's one sort of the most sort of well-pronounced phenomenon. But then if you look at, for example, these guys, like let's take a look at this one. Hopefully you can see that there are like some secondary peaks here, right? And these secondary peaks, they come out of training, right? So they probably are useful for the final performance of the network. That's why they appear. But in some sense, it means that indeed there are some kind of long-range correlations inside this energy attention operation. So it's not just one token looks at its immediate neighborhood, but there are actually like some kind of long-range correlations. So think about it like this. For example, if you see a head of the tiger in the top left portion of the face, there got to be a tail somewhere, right? So there has to be like a long-range correlation. And since we are sort of in the biophysical audience, I always like to point out these secondary peaks, and I want to bring up the very high level analogy with grid cells. Of course, like these things are very different from grid cells. They are not hexagonal. There are many differences, but in some sense they do encode the information inside the two-dimensional plane in some way that sort of has like multiple peaks. And in that sense, there might be something interesting about this. I don't know. So positional embeddings, right? So we're done with those. They're meaningful. They have all kinds of interesting correlations. Same trick. Take the matrix Xi, like this matrix. And again, it has a vector index. For that reason, we can visualize it in the image plane. So if we do that, then we get these kind of things. So these are some of the memories Xi's. And to answer your question, right, like these, things, they don't look like images, right? They look like some kind of, building blocks of images. They look very similar to the kind of early filters of CNNs that, like Rob Ferguson and Jan LeCun were studying, several years ago, right? So they are some kind of building blocks, but they're not like images themselves. But the cool thing is that here you can look into them. And in CNNs, you can also look in them, but in like conventional VITs, it's harder because you cannot look at them beyond the first layer. So the last thing regarding interoperability that I want to emphasize is that you can visualize the contribution of different modules inside the into the computation. So here, what you see is the same trick. We take the outputs of the attention module and the output of the Hopfield network module and project those outputs into the image plane. And again, everything that I'm about to describe sort of follows from the general theory, but it's nice to actually see it with your own eyes. And what happens is that if you focus on early times in the relaxation on the energy landscape, if you start with a masked image, right? Initially, the Hopfield network module doesn't really do anything. So it doesn't really add any information to those mask tokens. They were gray, they remain gray. But look at the attention operation. Attention operation provides a lot of meaningful information to the mask tokens because it routes the information from the open tokens. And it says like, because I see a leg of a dog here, there got to be something related to that leg in the patch nearby. So like the attention module does a lot of work early in dynamics. On the other hand, if you focus on the wait time in the dynamics, perfect. Okay, I'll wrap up. If you focus on the wait time in the dynamics, you can see that the situation is the exact opposite. So the attention produces some kind of, completely, not completely, but largely irrelevant contribution to the final output. And the whole job is being driven by the Hopfield network module here. So essentially, the Hopfield network module makes every patch very crisp and well pronounced. So it adds like resolution and like fine-grained details. So in some sense, and that's kind of what we would expect, right? So the attention routes information from things nearby, and Hopfield network reinforces that knowledge. That's what the sort of outcome from this picture is. Okay, so let me just very briefly mention a couple of related ideas. Same architecture, energy transformer applied to slightly different task, like very practically relevant task which has a lot of business value. Imagine, for example, that you have a bunch of bank accounts and you have like every bank account, a lot of features about bank accounts, like how much money is there, when the bank account was open, et cetera, et cetera. And you also know which bank accounts transact which other bank accounts. And you can take all that information and build a graph. And that's what this graph is. So essentially, every node in the graph is a bank account and every link in the graph is a transaction between the two bank accounts. Now, you can ask a question. Most of the bank accounts are doing good things, but some of them are bad. They do like money laundering, illegal gambling, et cetera, et cetera. Can we somehow automatically and very quickly and ideally on devices with like very, very memory efficient models figure out who is a good guy, who is a bad guy? Very practically relevant problem, right? And it turns out that you can think about it in the following way. At the moment of time t equals to 0, you don't know which of the nodes are good, which is the blue node, or bad, which is the red node. And then you run it through the energy transformer dynamics. And you are trying to figure out to find those red nodes inside this very complicated network. And it turns out it's, it's a perfect setup for these kinds of, network that converges to the final fixed point attractor state. And, on very quite sophisticated and quite big data sets, for example, T-finance and T-social are like very sort of decent size industry standard data sets for this task. You can see that energy transformer is the state of the art. So indeed, like in many situations, it actually does not only possess sort of theoretical, insightful value about what these networks are doing, but it actually works quite nicely in practice. Rushing forward, I want to very briefly mention one last idea before I wrap up. And this idea is the following. And we call this HAMOX, which stands for Hierarchical Associative Memory User Experience. And let me explain what it is in a few words and why we have built this tool. So essentially, let's think for a second how we used to train neural networks, say 10, 20, 15 years ago, I don't know. Like when I wrote my first paper on machine learning, that's how I trained the neural network. So, so what you used to do is the following. You take a feed-forward neural network, right? You write the forward pass, and then you define a loss function. And then you take, a pen, a paper, you calculate derivatives, right? And then you write the back prop, the backward pass by hands, by calculating derivatives on the loss function. And then you put it in MATLAB, and then it does it for you, right? So that's how things used to be done. Of course, today nobody does this because we have autograph, right? So nobody codes the backward pass by hands. Like you just define the forward pass and the network use autograph to compute derivatives for you. The cool thing about our networks is that even the forward pass technically is defined through the energy function. So technically, you don't even need to program by hands the forward pass because it's just you can just use autograph. And that's what HAMOX does for you. So you just literally specify certain things about this network. You press a button, and the HAMOX generates both the forward pass for you and the backward pass. And everything is done in a completely automatic way. So there is one twist, and it turns out that it's a very sort of important twist mathematically that I didn't discuss today at all. It turns out that the right way to think about these networks is the following. It's not even the energy, which is the most fundamental object here, but it is something that is called the Lagrangian. And I saw Bill smile. I think he likes the word Lagrangian. Yes, and I do too. So it turns out that the right way to describe these networks is not only through the energy function, but through the Lagrangian for each layer. And there is some beautiful mathematics that tells you how to convert those Lagrangians into the energies and to nonlinear equations for the evolution. And essentially what HAMOX does is the following. You give it a computational graph. You define the Lagrangian for every layer. And you define how those layers interact with each other. Then you press the button, and the rest is done by HAMOX for you automatically with autograph. So it's an open source library written in JAX. Please take a look. There is a link here. And I really the kind of stuff that I've described today would have been completely impossible to code by hands without this library. So if you're at all into software engineering, by all means, please take a look at this. Like how many minutes? 2, 3. Okay, then now I'm just gonna wrap. Yes. So then let me just finish. So I want to emphasize 4 things. The thing number 1 is that if you want to try dense associative memories for your favorite data science task, it can be computational biology, can be some kind of financial task, can be large language models, etc., etc. So by and large today, there are any limitations on the amount of information that you can write down or store in dense associative memories, or sometimes people call them modern Hopfield networks. So essentially like those limitations are gone. And you might be limited by some other properties of these networks, but at least you will not be limited by the insufficient memory storage capacity. For any specific data science application that you have in mind, there is a model inside the dense associative memory family which is quite likely satisfy your needs on that front. So dense associative memories can be continuous, they can be binary. There's absolutely nothing specific about binary networks. They can be perfectly continuous. You can train them with backprop, you can train them with Hebbian learning, you can just literally embed patterns into them. All these options are on the table. And all these options for training, they are completely decoupled from the architectural structure. So again, like this is kind of, a very cultural bias that I have to deal with a lot. Because many people, when they hear the word Hopfield networks, they immediately, their associative memory evokes things like Hebbian learning. But kind of, things like backprop training, for them, that's already not a Hopfield network. Like from my perspective, Hopfield network is an architecture. How you train it, it's your choice. You want to use backprop, use backprop. You want to use something else, use something else. That's perfectly fine. So dense associative memories can be also very complicated and very powerful in terms of what they can represent. You can make them convolutional. You can add pooling layers to them. You can add attention. All of those options are present, and we have, wrote many papers about how to construct such networks. They can also have many hidden layers as well. So that's all these options are on the table. And lastly, I really believe that this sort of, general theoretical framework for thinking about energy-based attractor networks with memories and fixed point, etc., can be a useful inspiration for building novel AI systems. And that's what, many people who work with me are excited about and what we're trying to do. Yeah, so thanks for all your questions.
Okay, so we should get started. It's a real delight to introduce our second speaker, John Cohen. John is a cognitive neuroscientist, and he was one of the founding directors of the Princeton Neuroscience Institute. And John's interests are very broad, as evidenced by his list of collaborators, which includes pure mathematicians, engineers, physicists, neuroscientists. And John has done some foundational work on the mission of cognitive control, maybe some of which we'll hear tonight or today. But more recently, John and his colleagues have been focusing on a very long-standing and fundamental debate in computation, which is how do you reconcile the benefits of symbolic processing with the efficiency of remote computation. And in this direction, John and his colleagues have some really interesting prescriptions for where to take the next generation of machine learning models. And so we are in for a pretty interesting talk. John, it's all yours.
Thanks, Kamesh. Thanks for being one of those many collaborators. In fact, there are several in the room. They're listed. Some of them are listed here. You've been hearing from them. So it's really a privilege to be here and also to have my colleagues here with me. For the psychophysicists in the room, you'll realize the danger of asking somebody who's used to giving 30 and 60-minute talks to give a 90-minute talk. There's this notion of the coefficient of variation having to do with estimation of time, like temporal interval estimation, which is that your ability to estimate time goes up as the variance in your ability to estimate time goes up as the length of time you have to estimate. So I'm already bad at estimating how long I have for a 60-minute talk. And so for a 90-minute talk, it's likely to be much worse. So I have no idea whether I have the right amount of material, especially given the audience and sort of the fact that this is a relatively new talk. In fact, much of the material is brand new. So having already wasted some of those minutes, and one apology, let me add one more and say, as Kamesh said, I'm a neuroscientist / cognitive scientist. And so you're going to be hearing a talk that's coming from a very different perspective. It won't be anywhere near as precise or mathematical, at least in most cases, as the one you just heard. I think it offers a complementary view of how these systems both can be informed by and can inform the development of machine learning algorithms. And I was actually surprised in listening to the previous talk at just how closely related some of the ideas are. And maybe we'll get a chance to explore that in questions and interactions. Again, I wasn't sure about the audience, and I consulted with Kamesh, and he assured me that it would be a good idea to say something about the history. As I said, I'm coming at this from the point of view of a cognitive scientist and a neuroscientist. And in today's world, the impact of machine learning and AI is obviously just incredibly strong. But I think most people view it as something coming out of computer science, and maybe neuroscience is relevant in the sense that the word neural is in neural networks, but you don't even hear that. You hear deep learning, right? Like, where does deep learning come from? Well, it's these machine learning algorithms. But in point of fact, there's a pretty rich history of interactions between neuroscience, cognitive science on the one hand, or psychology, and mathematics and computer science on the other hand. From the very beginning, when Turing first, proposed a mathematical theory of computation, it was picked up by people interested in the brain and how the brain might do computation. And McCulloch and Pitts were among the first to sort of formalize their notion of what it meant to compute in the brain. They were very much inspired by Turing. That gave rise to notions later, like the perceptron, and in computer science, and reinforcement learning in psychology and in neuroscience, which in turn sort of fueled developments like temporal difference learning algorithm, or what's now referred to as reinforcement learning in sort of machine learning. The backpropagation learning algorithm was actually discovered multiple times, and I think many people in this room probably know it's been discovered many times in the course of the history of engineering and mathematics. But most recently, in the context in which it's used, it was discovered by a psychologist, David Rumelhart, and Jan LeCun, who I guess is sort of a half-breed. It was really the impact that Rumelhart's discovery of it, and then Jeff Hinton picking it up, that I think drove a lot of what is now referred to as deep learning. And so we have the modern era of deep learning, but at the same time, tremendous progress in neuroscience and psychology that's been fueled by these technologies as well. So there's been a tremendous amount of interaction all along the way. And I would say what we see today is really a product of that kind of interaction. And so it's a privilege to be here sort of witnessing an example of that, given the breadth of people that are in this program that I think are interacting in ways that I think is what's most profitable in science. So, sorry, a little bit more recent. So one more sort of slight quick background point. There was a sort of major wave in AI. I don't think they really called themselves machine learning because there wasn't much learning in it. From when symbolic computing first sort of got realized in hardware in an efficient enough way to do something with it. And so those who are older in the room will probably recognize the term expert systems. It's not a word that's bandied about much these days, but it was based entirely on the notion of symbolic computing. And I'll say a little bit more about what I mean by that in a few minutes. It's sort of disparaged now because it didn't achieve all the lofty goals. And in fact, there's a term AI winter, which sort of followed the initial interest and explosion of interest in expert systems and symbolic computing, applied to artificial intelligence. But I think there were some really fundamentally interesting and important achievements. That, of course, was followed by the more recent second wave that involved neural networks or connectionist learning algorithms and deep learning, as it's sort of come to be called popularly. So this sort of, and these are largely disjoint. They were disjoint historically, and I think for the most part, they still remain sort of disjoint in terms of practice. There are still people doing symbolic computation, believe it or not, despite what you read in the New York Times. But they don't talk much to the deep learning people and vice versa. And I just want to take a moment, to give due credit to the symbolic approach. I mean, we wouldn't be running these algorithms on our machines if we didn't have it. It's incredibly, it's provably computational in general in some cases. In that sense, it's incredibly flexible. And one thing that's never discussed is it's sort of an existence proof that the human brain, despite what many connectionists have argued, is capable of symbolic computing. I mean, after all, symbolic computing came from the brain. We don't know of any other species or agent out there that came up with symbolic computing. And if you argue that you have to have something that understands how to do it, well, this can do it. And so I think that's sort of an important thing to keep in mind. And I think it's also an important sort of goal or aspirations to understand how it does it. On the other hand, there's a reason that expert systems and symbolic computing sort of ran aground, at least in certain kinds of tasks that people are really good at. Things like vision and natural language. There's a time when I used to sort of stand up here and say, I'm a connectionist and I'm studying things that the computer scientists can't possibly do. They can't get a device to recognize a face, and they can't get a device to recognize handwriting, and they can't get a device to understand language. Well, none of that's true anymore. So I can't say any of that. But I can't say that because of largely neural network achievements and not expert systems. And so symbolic computing really does run aground on certain kinds of problems. I think we know that now. Why? Well, it's inefficient in a number of ways, but maybe the most important one is it's hard to configure. And that's why deep learning works so well. It's really hard to program. You might be able to get a symbolic device to do natural vision, but the programs are so complicated that it just becomes impossible. And one might argue that it's just sort of intractable in a more principled sense. And so we have the miracle of deep learning. Computationally efficient. Often it's been referred to as an automated form of function approximation. By that, I mean it sort of fits a function to a particular data, and that's both its strength. It can do it incredibly efficiently in parallel. It can learn to do it, so you don't have to program to do it other than to sort of give it the data set and write down the objective function. But at the same time, it's sample efficient. You got to give it a lot of data if you want it to do anything interesting, and I'll come back to that point. And it's domain specific. So AlphaGo is really good at beating Go masters, but it's not very good at playing chess, no less, diapering a baby. So where does that leave us? Well, this is sort of the way it's been. Should it be a symbolic computer? Should it be neural networks? What does the brain do? And really, I think, again, the brain is an existence proof that it should look something more like this, like these things coexist. And we want to find how they relate to each other. How does the brain manage to sort of achieve both of these in a single architecture with the kind of robustness, flexibility, adequate enough efficiency, adequate enough competency to be able to do all the things that we do? And I think there's one way of characterizing sort of just how unique the brain remains. Even though I can't say that the brain is best at recognizing faces or playing chess, I can say it is still unique, and it's in this respect. If this is a simple sort of qualitative little plot here of a bunch of arbitrary tasks spanning both things that other natural agents can do and artificial agents can do: build a web, make a dam, play Jeopardy, navigate a car, and each of the colors is a different agent: spider, a bird, beaver, person, deep blue, AlphaGo. And what you can see is that for any one of these tasks, you can find some agent out there, natural or artificial, that beats people. Well, maybe not driving cars, although those who wrote up with me might be convinced otherwise now that automated navigation and driving is getting pretty good. But even if you don't accept that, we're pretty much beat at just about anything else. A spider can build a web much better than me or any artificial device. And obviously we know that artificial devices can play chess better than any human. But if you connect the dots and you ask what's the area under the curve, it's not even close. It's not even close. There is nothing out there, certainly no other natural species that we know of, a natural agent. And I think it's pretty obvious, no artificial agent that can do all these things with the level of competency that we can. So we have an incredible combination of flexibility and efficiency. And the efficiency comes in a variety of ways. Flexibility is sort of obvious. One is that we're incredibly data efficient. So some have estimated that for GPT, whatever it was, GPTX, I think it was GPT-3 that this was for, so maybe GPT-4 is worth, to sort of have the same amount of experience that GPT-3 had, a person would have to basically be reading everything that was written since the time of the Egyptians. And yet we managed to accomplish maybe not quite the level of GPT-3 in all respects, but in some ways maybe much better at other things in a single lifetime. And so there's just a radical difference in data efficiency or sample efficiency. And a lot of that comes with a certain amount of training. Some of it comes with no training. We can sort of generalize zero shot from having learned how to do one thing to learn how to do another. There's another sense in which we're incredibly efficient, and that's just in raw energy consumption. It's been estimated the brain runs on about 20 watts. I don't know what the estimate of the GPT-3 computer is, but it's got to be in the megawatts. Does anybody know? I'm sort of curious. I keep meaning to look this up and I keep forgetting. Anyway, many, many orders of magnitude more. And now that's a super interesting question. I'm sure it has a lot to do with the biology and sort of chemical computation. It's obviously an area of tremendous interest as we sort of reach the end of Moore's law. But I'll argue that it's not just the hardware that gives the efficiency. There's something about the algorithms that are still failing to capture the efficiency. And you heard a little bit about that in the last talk, and I want to make an argument from a slightly different angle in many ways, I think maybe complementing what you heard about in the last talk, in this talk. So how do we accomplish this? Okay, well, the challenge then is to integrate the flexibility and the efficiency, the flexibility of symbolic computing in tradition, as with an example being traditional architectures, with the efficiency of function approximation in neural networks. And there have been a lot of recent efforts to start to do this. And I think they roughly break down into two camps. One is what a group that calls themselves the neurosymbolic approach. That's one of these terms like neuropsychology that gets used in different ways by different groups. But the way they use it is to say, well, we're going to start with the premise that the brain has symbolic computing capabilities, at least at a primitive level. And this is built on arguments, well, dating back to arguments like Chomsky, that the brain has, genetically wired into it the capability for universal grammar, and it's just a question of figuring out what the grammatical rules of a particular language are. Through more modern developmental psychology, which argues that infants have certain core capabilities like object constancy that suggests that they must be doing some kind of symbolic computation way earlier than you could imagine them having learned it. Nobody's ever actually proven that. I'm not even sure how you would prove that, but that's been the contention. And then more recent incarnations, like program induction, that build on this by saying, well, look, okay, let's assume there are symbolic primitives. There's still a really interesting question. How do you write the programs? And that's been, of course, one of the problems with traditional computing, which is you have these primitives, but how do you put them together to do interesting stuff? Well, let's throw deep learning at that. So we'll give it the symbolic primitives, right? And then we'll throw deep learning at it. And a lot of progress has been made there in doing that. And maybe that is the way it works. Maybe there's certain things in the brain that are sort of there that one can recognize as sort of symbolic forms of computation, and it really is all just about learning. I don't want to dismiss that. There's a variant on that that I think I'm even willing to accept, but I don't want to take too much time to get off on that tangent right now. But if anybody's interested in that, maybe we can come back to that. Rather, though, I'm going to start with a stronger claim that falls into what I call the neo-connectionist camp. So the original connectionist camp was it's all learning. And anybody ever hear the light bulb joke about connectionists? How many connections does it take to screw in a light bulb? None. If you wire it right, you don't need the bulb. So if you laugh, you understand connectionism. That's a radical form of connection. It says all you have is a learning algorithm, an undifferentiated spaghetti of connections, enough units, and a lot of data. And, first approximation, that's sort of what transformers are. I mean, they have some interesting technologies and some constraints. We'll come and talk about that a little bit. But, the basic idea is you want to basically get everything through end-to-end training. And I'm going to try and toe close to that line in thinking about how you can get neural networks to do symbol-like or perhaps even genuinely symbolic computation, sort of in this spirit, but with a slight addition, which is that we're going to add some inductive biases, and in particular, structural ones. We're going to add certain constraints on how the thing is built that are genetically coded. They're not constraints that say you have to compute symbolically, or that, in any event, it doesn't give you the symbols with which to compute, but it strongly induces the system to try and discover abstract enough representations that maybe we can convince ourselves to call them symbolic. That's not to say that training doesn't matter. Curriculum is critical. I'm not going to talk a whole lot about that in what I prepared. But again, if people are interested, we can talk about that. There are people in the room who can say a lot about that. So it really is a combination of curriculum, maybe given to us by culture, what machine learning people often call meta learning, but critically an architectural constraints that bias the system towards the discovery of abstraction and thereby perhaps the emergence of symbolic computing. Yes, absolutely. Please jump in. Yes. I mean, that's one way. There are many ways that you can play this game. That's one. Sure. I mean, it depends what you mean by tokenization. If you just parse it into letter blocks that happen to be words, maybe not. But if you structure them and you put you put, for example, carefully crafted positional codes in there to in basically give the system the knowledge as to what part of speech it's in, that's right. Then it's more like neurosymbolic than neo-connectionist. Sure, no, go ahead. I mean, for a given problem, presumably, there's not necessarily. I'm not sure that one has to assert that. I mean, I don't think I'm qualified to answer it, but I don't think so. Somebody's shaking their head. That creates a new symbol. Right. Could be. Yeah. I have a word to say about something that's closely related to that. I think the base counting story is maybe pretty close to that. And that helps. We can dive on that later. Yeah.
Just like the point later in slides, you were just asking for kind of one of the conditions for small computers.
You know, I hesitate to do that because there is none, as far as I know. We've had endless arguments about this in our group. I'm going to give you an example of how I would diagnose a system as having done something that's identifiable, at least as best as anybody I can find would agree, definably symbolic in that case. Whether there's a general, the problem is that the general notion, okay, so maybe I'll take a quick moment to say this. In the purest sense, symbols are just labels. They can be assigned to anything, okay? And in that sense, the extension, it's an extensional commitment that this thing can be anything. Dog could have meant anything. It could be tree, house, barky thing, whatever, right? Square root of -1, we could have called dog, right? So dog is just a symbol that's a label. That has no structure to it, right? That's, you can think of that as sort of a field or a determinate point process, right? And it's clear that in computing, that's not enough. You have to be able to do more, or certainly for any kind of efficient computing. And so often you end up, so pointers are symbols, right? You can have an address that points anywhere, but then you see sort of the incursion of things like pointer arithmetic. Like, let's put all the things that are that need to be computed together near each other, and we'll know sort of what order they're in. And it's still symbolic in the sense that you're using indirection and have pointers, and you could put anything that falls into a particular category in those locations, but it's not quite just a pure label, right? And so it's a bit of a slippery slope. And Alan Newell has a nice treatment of this in the physical symbol system, in his paper about the physical symbol system hypothesis that I would refer you to, that I think probably does the best job of doing as good as one can in inventorying all the ways in which people use the term symbolic. But I'll give you a concrete example of at least one way, in fact, this labeling function, where I think we could all agree that it seems to be symbolic. And I'll unpack that a little bit more when I get to it. Okay, one of the promises, if we can achieve a neural network that self-organizes and has at least a piece of it that's symbolic, is that it makes it more, more comprehensible, more explainable. One of the problems with deep learning, I think it was said in the last hour, is that you train up these transformers and you don't know where to look, and especially since I like to say backprop is a cat. You train it to do one thing and it goes and does something else, and when you see what it's done, it's like, oh, that's what it was trying to do, but it's not what you wanted it to do. It goes and hides under the couch or something. And in that sense, I think, backprop leads to unexplainable AI if you don't have some kind of structure. I mean, we heard of one kind of structure in the last talk where you force the weights to sort of be shared, and it starts to force it into lower dimensions, and that forces it, I would argue, to abstract more, and therefore you start to interpret it more. And so that's sort of on the path to the kinds of things we're looking at or looking for. Okay, so in this talk, I'm going to talk about two features that I think are going to make neural networks, or that are needed to make neural network architectures more human-like. That is sort of better combination of flexibility and efficiency. Roughly speaking, they're going to address abstraction and autonomy. I will say what I mean by autonomy later, but I guess this, and the next slide will give you a little hint of what I mean by it. I think each of these is going to require two kinds of capabilities, and that's what the talk is arranged around. So the first is this notion of relational bottleneck, and I'll unpack what I mean by that. But the argument, sort of the take-home message, will be that if you introduce one very simple structural constraint in neural architectures that induces what we call a relational bottleneck, you start to get what looks like symbolic computing. And at least in some cases, I think can be defensively argued is symbolic computing. And the other is the capacity for self-reconfiguration. We have the capacity as individuals not just to be trained up on things, but to decide what we want to be trained up on, when and how, And that in turn impacts how good or bad we are at things. So I can decide if I want to type to do hunt and peck and learn how to do it quickly, very flexibly. I can use that same algorithm for doing, working on a keyboard on a computer or playing on a piano, but it's not very efficient. And so if I decide that instead of just hunting and pecking, I want to be a stenographer, instead of just entertaining my like 6-year-old niece, with Twinkle Twinkle Little Star on the piano, I want to be able to play Mozart, I have to invest a lot more time to become much more efficient, more parallel, use all my fingers at once to do things like play chords or to touch type if I want to become a typist. So that decision about how to configure myself is something that has been looked at least in small parts of the machine learning world in terms of active learning, but it's a very, very thin and I think very underdeveloped area. And it's something that, you're doing it right now. Here you are. So I think we need to figure out how that happens, and I'll have a word to say about that. Okay, so let's start with the relational bottleneck. The goal here is to induce neural networks to learn more abstract representations. What do I mean by abstraction? Well, low dimensional structure, the ability to capture what is of essence in a data set that allows me to both deal with that data set in an adaptive or useful way, and at the same time, be able to apply that in other data sets that have the same structure, which means that all the other sort of incidental features of the first data set were, well, incidental, right? So I captured sort of the essence, the structure. And as I just implied, that's usually defined or evaluated by the capacity for generalization, to take the information that I've learned in one, or the structure that I've learned in one setting, and see if I can apply it in new settings. Now, usually, this is done by training a neural network, giving an experience about the world, and then testing it for generalization, asking it to sort of perform on other samples. But this is almost always done, these days less and less, but for a long time, the main focus was on interpolation. That is, out of sample, right? You didn't see these little purple diamonds, stars, but you saw everything around them. So for these particular samples, I can say the one that's in the yellow patch is going to be yellow, and the one that's in the red patch is going to be red, and the one that's in between the blue and the yellow, well, maybe it should be green, right? I'll mix them. But in the real world, we have a bigger problem, right? We don't get to experience everything. And it could be that, when we want to predict something that's not in our range of experience, that is out of distribution, right? Out of the convexity. You can argue about what we mean by convexity. It's a whole nother deep dive. But in some sense, there's an envelope around the data we get to see. And the question is, how well do we do when we go outside of that envelope? And so here, what would I do? Well, that purple one is the closest one, so I'll call it purple. But, what if the world looks like this? I'm wrong. I got to call it green. But how would I have ever known that, right? And in fact, you probably couldn't. So the only way that you can know what to do with that star that's outside of your experience is if the world is something more like this. There's some kind of structure out there that comports with the structure that you've been exposed to. In some sense, it's part of the same distribution in a second order sense. It's part of the same structure, right? And so if that's the case, if I've seen this, I could guess orange, right? And what that really reflects is that I've learned something about the structure of the data that is consistent outside of the range in which I've experienced it. And so let me just give you a cognitive example of this, and then I'm going to circle back and say a little bit more about this. And that is analogy formation. So how do people do this? Well, if I give you the analogy, an electron is to a nucleus as the Earth is to what do you say? Sun? How many people think sun? Oh, good answer? There's hesitation because you know that I'm setting you up. Sure, why not? Sun, right? Why? Well, because electrons orbit around nuclei and the Earth orbits around the sun. So that's all fine and good. But it turns out that every once in a while you'll get somebody who'll say, no, Jupiter, right? Why Jupiter? Well, it turns out it's a better answer by any sort of mathematical, well, maybe not better, but it's as good an answer. Because Jupiter, it's better with regard to linear structure, right? Because Jupiter is about the same size bigger than Earth than a nucleus is to the electron. Why? Well, thank you. That's exactly what I wanted to say. So that's exactly right. How you answer this question depends upon the structure that you inferred in the data. And if that structure comports with an answer, then you can give it, right? Because that's what it means to extrapolate. There's nothing about nuclei and atoms that, at least as far as we know as physicists, at least as far as I know, having taken physics 101 in college, has anything to do with the Earth and the sun in terms of the relationship of one to another, right? other than these kinds of sort of macro structure. And so we extract structure. We can call it a relation, right? Linear, orbital, or perhaps gravitational. And what we'd really like to do is define these things in terms of functions and ask what function can you learn over the data, right, that will stretch out and apply beyond the space, or what function that you know of fits one set of data that you now need to fit to another. And this has been studied explicitly in psychology in terms of function learning and capacity for extrapolation. So people are given sort of the blue portion and then asked to complete the orange, and they can be pretty good at it. And the neurosymbolic approach has taken a stab at this, and it basically says is, well, we have in our heads a bunch of functions, basis sets, right, that we can call Gaussian processes, and we're going to fit them to the data. And once we figure out the one that fits the best, we'll just use that to do our extrapolation. And it does a reasonable job. It fails in certain critical situations that Simon here can tell you about. This is work the empirical work in the Gaussian process model is work that Sam Gershman and Josh Tenenbaum and his group proposed. And they did some experiments and provide some support for it. And Simon here has done some simulations showing both where it works, but also where it fails. I'll let him answer questions about where it fails. But the big problem here is that it is exactly in the same strategy camp as the neurosymbolic approach, right? They didn't present it that way, but it's sort of the same deal. You have to pre-specify the basis functions. The system doesn't learn those functions. It's given those functions, and then it does Bayesian inference over which is the function that fits the data best. Okay? The connectionist approach would learn the functions. And in fact, that's exactly was the force of Simon's work, was to see what kinds of models could extract such functions. What are the simplest models we can build that would extract such functions? And we've had some success using autoregressive models, RNNs. Zach Dahlberg, who I don't see where he is, but here he is. He's done some work with iterator models, and we can get them to do reasonably well. But once they run out past a certain range, they start to fail. Okay, they accumulate error. So they look something like this. Like they get the oscillatory dynamics, but if you ask them to continue to iterate, to run the function sort of out past the range that they've been sort of trained on, they start to become inaccurate. So what do we really want? Well, what we really want are what the physicists have called symmetry functions. In fact, it's been said that it is only slightly overstating the case to say that physics is the study of symmetry. And I want to add, it's only doing slightly a bit more so to say that's true for cognitive science. What we're really looking for, if we want to understand the human capacity for abstraction, has to be the study of symmetry functions, because other ways, there's no way to extrapolate. There are ways to make guesses. There's this notion of elliptic distance, I guess. So if you have functions that are good enough, they sort of have a penumbra of extrapolability. In some sense, that's what these learning algorithms give us. But they're not algorithmic. They're not symbolic. They don't have the function written. They don't learn the symmetry function itself. And that's really what we're looking for. And there's evidence that people do this. Well, I gave you one, but function learning is one place where people looked at this. Analogies, stereotypes, schemas. They're all examples of where people apply certain forms of invariance or equivariance that they've learned that are stable across some transformation. That is, they satisfy this at least broad notion of a symmetry function. And so one could argue that genuine extrapolation really requires the discovery of symmetry functions. And so then the question becomes, well, what inductive bias can we introduce into a learning algorithm that will promote such a discovery? To get to how we might do that, it helps to think about symmetries as relations, right? They're relations that obtain over the elements within the fundamental domain of the function that apply infinitely, and in some sense you can argue it almost has to be periodically beyond it. And so this property is one that's formalized in group theory well beyond my pay grade, but fortunately I have people who are good at this kind of thing, and so Kamesh has been leading a group beginning to explore what work has been done in group theory that can sort of define the kinds of operators that give rise to symmetry groups that might help inform us about what we're looking for in terms of what we want to get sort of neural networks to learn. The key point, though, is that it's the learning of relations that may help promote the discovery of such symmetries. And so the simplest relations are things like identities or local sequential structure, Markovian properties. Kamesh has coined the term correlations are all you need. I think that's a slight overstatement because it isn't necessarily correlations, but maybe if you allow different orders, one can make that argument. But you want something like this that learns sort of the second order statistics of the system and is biased to learn those and learn those alone. And from a psychological perspective, it might look something like this. If you want to understand that, the sequence on the left is ABA, and it's the same as the sequence on the right, which is ABA, then all you really need to know is about the similarity structure within one, and then you can generalize it to the other, and you almost don't need to know what the items are, as long as you can sort of process and do the identity computation, right? So how do we build this into a network? We'll argue that it's through the use of what we call a relational bottleneck. And this relies on the use of external memory. And to give you an example of what I mean by that, it was discussed briefly this morning, but I'll be slightly more explicit about here. The notion of external memory is there are a lot of ways to define external memory. The way in which we're interested in it is a form of memory where you can store things that have the properties, A, that when it's stored there, it's latent. It won't do anything. It won't have any impact unless you go and retrieve it. Another way of saying that is it won't impact the structure of the part of the system that actually does computation. It just sits there sort of outside of the system, as opposed to, say, the weights inside of a neural network, where the minute you change those, it's a form of memory, right? But it changes the computation. External memory is where you can put something and it won't change the computation unless you go and get it and use the data that's there. And secondly, that is someplace where you can put pieces of information that otherwise may have no relationship to one another, but will be bound to one another. So when you retrieve one, you get the other, right? So if I say to you, window and reason, remember those two. You've never thought window and reason together. But in 5 minutes, if I say to you, what was the word I said for reason? You can say window. If I said window, you could say reason. And I said it that way because although we often think about dictionary, external memory, and we usually implement them as simple dictionaries, literally Python dictionaries, right? Where there's a key and a value and you retrieve by the key and it's the value you get back. In reality, it doesn't really matter whether you label it as the key or the value. I think that was said in the previous talk as well, right? What you really care about is that there's two representations that are now available for retrieval out of the scope of what's being currently computed unless you go and get it. And that if you get one part of it, you'll get back the rest. So the critical features are the rapid binding of information and then the capacity for retrieval. And usually this is done in a similarity-based way, that is through an inner product. And this is pretty much exactly what the attention head of a transformer is. So there's a very close relationship between how you use external memory and what transformers do. And I'll be explicit about that in a few minutes. In this kind of thing, there's no reason you can't have window as a key and window as a value, right? I mean, no. Think about these as literally, and this is a pretty useful implementation. Most of the time, this is the way it's implemented. It's just a long concatenated list of vectors, where the vectors themselves are concatenations of the things that are being stored. Okay, so the rows are just these stored values, and then you can think about the rows as being comprised of fields that are accessible and retrievable. Okay. This is an interesting question. Like, how many fields do you have, and how do you construct that? Those become interesting architectural features, but in principle, there's no limit. I mean, in practice, of course, there is, and how you limit that becomes a really interesting architectural design element. But you'll see, none of this is critical to what I want to say. I mean, they're fair questions, but they're not. They're reasonable hyperparameters, but they don't get at the core of what we really want to do, which I'll show you in a minute. Okay, so this implements, by the way, a form of episodic memory that has been, in fact, the inspiration for DeepMind was the idea that this kind of external memory may be one of the functions of the hippocampus. For those who are familiar with complementary learning systems theory, that says that, the reason we have a hippocampus is to be able to do fast learning so that we're not subject to catastrophic interference in our slower learning, statistical learning neocortex, right? So if you want to, for example, know where you parked your car today, you don't want to encode that that's where you parked your car today and then think forevermore, oh, that's where I always park my car. You sort of want to have this statistical knowledge. Where do I usually park my car? Where's where most people park their cars, separate from where you parked your car today, right? And there are formal treatments of this, and there's a very rich, corpus of theory now about this is why you have a hippocampus. It's sort of to protect the neocortex, which is doing statistical learning, while being able to encode things really rapidly. And Demis Hassabis sort of saw this and said, wow, that's a really cool idea, and it's not being used in machine learning, and at least part of his inspiration for forming DeepMind, even though that's not where the initial successes came from, was exactly this observation. It also, I should say, when you implement it as a dictionary, it's a convenience because Python has dictionaries. It doesn't have Hebbian learning mechanisms, but I think we can plug in a Hopfield net with Hebbian learning as a very plausible neural implementation, and I'll say a little bit more about that in a few minutes as well. Okay, so here's an example of what I mean, and this is, in fact, out of DeepMind. This was, in many ways, I think, the most interesting paper, not technically, but conceptually, that came out of DeepMind. And it was to say, look, let's actually do this. Let's couple an LSTM controller, so some sort of mechanism, could have been a transformer. In fact, people are now working on putting transformers in place of this, with an external memory and see what it can do. And you can think about the external memory as a sort of Turing tape. It's a place where you can literally write things down and then go back and get them when you need them. And so they showed that if you do this, you can actually get neural architectures to start to do things that are very symbol-like. And they have a paper about this. I think it has 80,000 hits. It was really, really, I think, I think it was a breakthrough. I think it was really a major contribution. The problem, though, is that sort of like transformers, and one can argue this is a notational variant of a transformer under certain parameterizations. It's incredibly data efficient, so inefficient. It took like, God knows, hundreds of thousands of trials to get it to learn to do a copy operation. And so just like transformers, it's capable of very powerful stuff, but you have to beat it over the head to get the abstraction. And we were playing around with this, and we had some thoughts about how one could use these to do interesting abstractions, and we were starting, and it wasn't working. And then a student, a computer science student, working with a postdoc in my lab, Taylor Webb, student was Ishan. Oh my God, I'm embarrassed. I forgot his. Sinha, thank you. I forgot his last. He's gone on into industry, so I have a right to forget him. Taylor, on the other hand, is on the market. So if anybody wants an amazing, amazing young scientist, Taylor Webb is really quite remarkable. Working in the sort of cognitive part of the space. Anyway, they had the idea that what if, instead of having one controller, we had two? And the inspiration for this was that one controller in the neural Turing machine was responsible for both the encoding, the control, sort of having working memory in the LSTM, and then decoding, generating output or actions or whatever, and also managing the Turing tape, right? Knowing when to write, when to read, how to sort of, and all of that was sort of munged together, just like it always is in connectionist spaghetti in this LSTM. And the thought was, well, maybe it's just, if we just sort of pulled apart, we exploited the external memory to pull apart the part that had to learn the abstraction, right? In fact, sort of turn on its head, it can only learn abstractions. Maybe that would work. And so what we did is we put a controller on the other side, and they're labeled again here as keys and values, but that sort of belies the fact that either side can either write or decide to read. When they write together. When one reads, the other one gets back what was bound to what the one that read retrieved. So if this thing writes an item here, and then later this thing decides to retrieve it, this is what this part of the system gets back, okay? So I'm not going to go into the details of how it all works. And to be fair, there's still a certain amount of magic in these models where, as the modeler, we decide when things are writing and when things are reading. We're now working on models that learn how to do that on their own, and there's been some success with that. But for the moment, we're just going to ask, if we get to decide when this thing should write and when it should read, can it learn to do abstractions? The thought was that if it's set up like this, and we can differentiate through this external memory. That was, again, one of the things that DeepMind gave us, differential neural dictionary. It's all like many things that are fundamental and beautiful. They seem really obvious in retrospect, but nobody had done it or thought of it beforehand. So we can differentiate through all this. So we can train it either on loss here. The version I'm going to show you, it's trained on loss here, but it doesn't matter. We've actually done it exactly, training it on loss here, meaning you put the inputs here, this whole thing crunches through, sequence of stimuli. It has to give the right answer over here, and we differentiate through the whole thing. then, this thing is seeing the data and it has to generate output, the form of data in some sense. What can this thing possibly learn? Whenever this thing writes here, right, it's bound to something that's written here. But this thing never gets to see what was written here. And conversely, this never gets to see what was written here. So if I'm running this and I train it, what can this thing possibly do? It never gets to see the data. But if things happen, for example, in the right sequential order, then this starts to get a sense of order. And if it learns to write things and it can write things and then it's given responsibility for retrieving at the moment, then it can start to learn the sequential relational structure over here, right? Now, that coupled with the fact that these retrieval operations are similarity-based gives it a way of learning relations among these, whether they're sequential or otherwise, okay? That is entirely, it can only be abstract. It can't be the data itself because it never gets to see it. It has to invent representations here that allow it to do the task without knowing what the data themselves are, okay? It only has access to second order information. And so it turns out that this isolation, coupled with the similarity-based retrieval, implements what we call the relational bottleneck. And that relational bottleneck allows it to learn genuine symbols. So let me give you an example of the first instance of this. And I think this is where I can make the argument that it really has learned symbols. And then I'll tell you a little bit more about some of the recent work, and then we'll get to the second part of the talk. How am I doing on time? Not too bad. Halfway in? Jesus, well, I'm not halfway through the slides. So we trained it up on a bunch of tasks that are commonly used in studies of abstraction and intelligence in human intelligence tests. In particular, the Raven's progressive matrices. These have become very popular now in machine learning for exactly the reason we were interested in them, which is what I just said. And we trained them up on a bunch of stimuli, just random Unicode characters. And we picked these both to be easy to implement, but as sort of non-structured as we could possibly make the stimuli themselves. So there's as little statistics in the data as possible with regard to what the task was. And we gave it a bunch of tests, same different task. Relation, match the sample, I won't explain, identity rules, like is this the same as this? And then the one that I am going to talk about, which is the distribution of 3, and I'll explain what that is in just a second. Okay, and then we pitted it against a bunch of other architectures. I think they're listed on a subsequent slide, and tested it at different levels of exposure to the training data. So I'm going to focus on the distribution of 3. So let's just look at what it looks like for that. First of all, so the models that we compared it to were a transformer, the neural Turing machine itself, a standard LSTM, and then a few other variants on feed-forward networks that had been designed specifically to learn relational information. Relational structure. And what you can see is that they all, well, except for the relational net, ironically, pretty much converge. But the ESBN does it like insanely fast, like maybe 50 to 100 epochs as compared to hundreds, if not thousands of epochs. And secondly, when we train it, we tested like how much of the number of those Unicode characters would it have to be trained on in order to be able to generalize to the remaining. So the 100% is like it's trained on everything. Like how well does it do? And that everything but that relational net pretty much nails it. But then we can take away 15% of the Unicode characters and say we train on the first 85% and then test on those last 15% and how well do they do. And most of them do pretty well. Things start to drop off at 50%. And at 5%, that's the smallest number of stimuli you can use to train that exemplify the rule. So it's like literally one example of the rule, period, right? One set of stimuli that it gets to see the rule. Now it sees it maybe 50 or 100 times or 1,000 times, whatever the number of epochs, batches are, but it only sees those stimuli. And nothing can do that. They're all a chance except for this structure. So that's the first evidence that it's somehow figured out what the rules are in a symbolic form. It can generalize from a single example to the entire rest of the space. Yes. Yeah. These were they were not rich images. They were I think they were just simple vectors, but they were sort of arbitrary random vectors for each symbol. They were the Unicode. Sorry, I might be wrong. The Unicode characters may have been like like a MNIST or a convolutional net filtered version of the thing, but it doesn't matter. I mean, the point is, as long as you can encode it and there's enough orthogonality among the stimuli, and in some cases you can relax that assumption, You just need to get the data in. And if there's any rule to how the data are being used, it picks it up. That's sort of the point. So let me unpack. Yeah, and here's the, yeah. I'm about to show you. Let me give you the example of the task, and then if you think there's more than one solution, I'd like to hear it. But I'm going to pick one task and walk you through it and see exactly how it does it. Not how it learns it. That would be a longer discourse, but what it looks like when it's processing. Okay, I'll walk you through that. There's no hippocampus in this. There's just a dictionary. In this model, there's no there's recurrence in the LSTM controllers. Sorry. In the particular model I'm about to show you, the embedding side was feed forward. There was recurrence in the LSTM, but it can be done with a transformer instead. So it can all be feed forward. There's nothing intrinsically necessary to be feedback. But if you want to implement the external memory piece of it, you can do it with a recurrent Hopfield net, right? So yeah, I think, yeah, this might be a question to take up offline. Yeah. Okay. Right. So this is what it looks like. Sorry, I should have explained the distribution of 3. So here's the distribution of 3. I say to you, circle, square, triangle. And now I say to you, triangle, square, what do you say? Circle, right? That's the distribution of 3. I give you a set. In this case, it's a set of 3. And then I give you 2 elements of the set, and I want you to tell me what the remaining element is. Okay? I can say to you, coffee, lectern, sky, lectern. You can do it over anything. Once you get the idea that you can label those 3 items and bind whatever it is that comes in to your 3 labels, and you have a way of retrieving and using the labels when you get the items and using the labels to retrieve those items, you can do the task. So that's what this thing learns to do in the abstract. And here's what it looks like when it's doing it. So on the right is the data, and it's set up so that there's 3 items of encoding, and then 2 items that are probes, and then a query item. And the way we did this, there's a variety of ways of doing it. We've done it several different ways. They all work. In this case, we're doing it the way people are actually asked to do it, which is sort of a match to sample or multiple choice. And you'll see how that works in a moment.
If you don't look at it, there are 2 lines. If you look at it as a block, and you ask what the last one you put, you could decide that you do the square. You could also decide that you have 1 rectangle, 2 triangle, and 2 circles.
You could. This is the yes. That's correct. Yes. No, that's right. I mean, look, as I said at the very beginning, the curriculum matters. Curriculum is fundamental, right? Here's a curriculum. People are pretty good at picking it up. Can we get a model to be good at picking it up? Okay. Okay, so what happens is and as I've said, here, we're the magician behind the curtain, pulling the strings on when it's going to encode and store and when it's going to retrieve. Next, one of the things we're working on now is getting it to learn that, but that turns out to be not that big a deal. It sees, and so in this case, it's going to use scanning visual attention, if you will. So it's going to look at the first item and encode a circle, and so it's just going to write a circle. Now, I'm showing you how it worked after it's trained. Right? Initially, the thing on the left, this thing here, doesn't know what to do, so it just writes some random stuff. But eventually it learns to write something. We'll call it A. Okay? And now it looks at square, and this thing writes B. And so A is bound to circle, and B is bound to square. And then similarly with triangle. And now it goes into encoding mode. Retrieval mode. So it sees the triangle, it encodes that on the embedding side, and it retrieves, it asks to find what is closest to what it's seeing. And so that's triangle, right? And on this side, when it retrieves triangle, this thing gets a C, right? So it puts into LSTM, I saw a C. And this thing is just a recurrent network that's keeping track of its recent states. So it has in memory C. And now it looks at the next one and it sees circle and it matches to circle here. So it retrieves A. And so now it puts in working memory, I've seen A. So I've seen C and A. And now it knows it's looking for B. It's learned to do this, right? This is what the thing on the left is learned. We didn't tell it to do anything. Random initial weights, train it up. This is what it learns to do. Okay. And now it's going to look through the options and say, okay, which of these options is the one that's going to correspond to B? So it sees a pentagon and it looks up stuff and it doesn't find anything. So there's nothing in memory there. Okay. And so it puts a question mark next to the first item. And now it sees a square and it retrieves square. And so it knows that it's B. And so it says, okay, B is the square. Oh, B is what I'm looking for. And so it encodes 2 as the thing that it was looking for. And now you can see what's going on here, right? A3, D4, and it goes back and says, okay, what was B associated with? Because that's what I was looking for, and spits out 2. So it solves the problem. And when we look inside of this and we ask, what do these representations look like? They are identical no matter what stimuli you give it on this side. And so I would say, in that sense, it's a symbol. X, Y, Z, A, B, C. I ask, I write a function, f of x, y is y minus x. And now I bind y here to some value here and x to some value here, right? I'm done. I mean, and x and y are always the same. It's the same 2 parameters, the same 2 arguments for that function. So this thing has learned to function with variables that it can bind to arbitrary fillers. Sometimes people call these roles. It's role filler binding. Okay. They only know that the keys, remember, there's sequential structure here. So what it knows is that I saw A and B, and the rule is once I've seen A and B, I need to look for C, or I've seen A and C. I have these 3 things in mind, these 3 labels, and as soon as I see 2 of the remaining 2 of the labels, I know to look for the third. That's all it's learned, those 3. And then once it knows what label, it simply does a retrieval, and whatever was bound to it in episodic memory gets pulled out. When you put an entry in here, it just gets rapid synaptic plasticity or something. In Python, it puts it next to each other in a vector, right? I mean, whatever the mechanism that does the binding, that's an interesting question. That's not of interest here. The key is, the relevant thing is that functionally, it's immediate and enduring. Unlike working memory, which is immediate and not enduring, and unlike really long-term memory, which is slow and enduring, this is immediate and enduring. That is what psychologists call episodic memory. So that's the sense in which this implements an episodic memory. It has the functional attributes of what we refer to as episodic memory. I parked my car. I can remember that right away, right? I can retrieve from it. I won't remember it forever, but it doesn't take me a long time to learn it. And I can remember it for long enough. Like you'll remember where you parked your car on a particular day for a few days at least. It's not fleeting like working memory. Sleeping is a more complicated part of the story. If you're sleeping in your car, well, sure, if you're there, but I'm saying if you walk away from it, you have to remember where it was. Yeah.
When they're presented in the circle, that over time,
over here?
Yeah.
That's a great question. In this particular case, it was the same every time. This model, depending upon how you tune this part of the network, this will either be forgiving of variation around it or not, right? So if the square is more similar, if the variant that you introduce to that square is close enough to a square, you might get a match. But if the softmax temperature is very low, then you won't. And so I refer to that as the semanticity issue, the question of how you categorize these things. And so presumably there's some part of the system here that learns how to categorize things in ways that's useful for their use here. And that turns out to be a really interesting part of the story. This relational bottleneck not only imposes the extraction of abstraction on this side, but that ability then feeds back into training up the embedding layer to do a better job of factorizing spaces in ways that makes it easier to keep things apart so that they can be used this way. That's a mouthful, but yes, so I said, and we have some simulations that show exactly that property. It's permutation invariant, but
the first thing that the way you said it, recognize that there's a triangle, then you choose. But what if the first round was the empty?
The order of presentation, either of the memoranda, the set, or of the probes makes no difference. The only thing that matters is that you present all of the memoranda together as a period, and there's some segmentation that tells you, okay, now I'm done with those, and now I need to start matching or looking for matches. That's still, in this model, the magician behind the curtain. Okay, so you have to know, you have to do what we would call event segmentation to know, like, when am I in the part of the event that's encoding the memoranda, when am I in the part of the event that's looking for the matches, and when am I in the part that's responding, right? That's still an issue, but right.
It's not a long path, but time, you know, the simple things are swapped out. Well, for unbind,
and super interesting question. If I understand the question right, then another way of thinking about this, or maybe a closely related issue that has forced us to think about unbinding, is how big this is, right? In the real world, how long is this, right? And we know in the human brain it's big. Often I think of transformers as being a sour spot with regard to the human brain. The inputs are everything it has available at the current moment to compute. And so in some sense, that's supposed to be its attentional window. That's absurd. You don't have 10,000 tokens worth of an attention window. You barely have 4, right? On the other hand, it's only 10,000, and that's all it has to compute with other than its weights, right? And, you know, we have more than 10,000 memories. And so it conflates, in some sense, the attentional window with episodic memory. And if you unconflate those and let episodic memory, this, be as long as you want, then you solve a problem. But, you know, can it be infinite? Is it truly like an infinite Turing tape? Well, this is an interesting question. In psychology, this has been debated for eons. There's a strong argument that you actually don't forget, that everything you've ever experienced in some form, insofar as you've encoded it, to the degree that you've encoded it, the precision and the inflections that are there in encoding, it's still there, right? I'm not sure everybody agrees about that. And there are ways to implement forgetting in something like this, where if you imagine that you keep track of all these records, and either you do usages, and people have theories about this, like reconsolidation, neuroscientific theories that claim that that's important, you have to use memory to keep it, or you just simply say, look, I'm going to, when I run out of space, only put the new memories sorry, you add a little bit of decay. So let's say you have 10,000 entries. Every time you add a new entry, you decay everybody by 1/10,000. That's almost nothing in the near term. But after 10,000, right now, the first one that came in is going to be weak. And so you take any new one and you put it there. Well, that means that you lose old ones. Well, if along the way you happen to have retrieved something, like maybe 5,000 ago, well, you retrieved it in a similarity-based way. So there's something about it that made it useful that's pretty close to its original state. You've now retrieved it. Now that's part of your current working memory state. You're going to store that, right? And once you store that, you sort of have an updated version of that old memory, reconstructive memory. This becomes sort of a natural way of both dealing with the infinite length, and I think one could argue is a pretty near normative way, if you have capacity constraint, that explains makes some predictions, pretty interesting predictions about psychologically relevant phenomena. So none of that's been explored, but I think this is a super cool question and direction to go. Yeah. Well, that's why I said what I just said. Yes, I understand. That's what I just said. But so if they die at the rate of the number there are, right? Like, so if you have 10,000, you only lose one every, you know, episode, then you can sort of be in this steady state. Yeah. I started, this is the first thing I said. We don't know exactly how memories endure and whether they endure indefinitely. It seems reasonable to think they don't. But I'll just say from a psychological perspective, people haven't had to invoke forgetting to explain the things that is loss of memories that explain people's behavioral signatures of forgetting. Forgetting is usually dominated by similarity structure and failure to retrieve due to proactive interference, it's called, rather than any strong evidence that the memory wasn't there. And there's evidence, there are lines of evidence that suggest that if you construct the probe just right, you can get really old memories that people didn't even know were there. Okay, so it is controversial. But I don't think it's settled one way or the other. It seems, in the end, physically, it seems, yeah, maybe. Indeed. Yeah, sure.
And just like we also put that like when you go for what you can and what if the relation actually exists in for example 30 unit codes, but like how would I guess the model is pretty well that or like
I'm going to say something about that in just a minute. Okay. I mean, we haven't gotten there yet. No. Right, but what all that would happen is the first circle would be to A, the second circle would be to B, the third circle would be to C. And now I give you one circle and you just pick a random one. You just need a bias now, not to pick the same symbol twice, right? And then I give another circle. So I've already seen A, so I'll just grab another one, B, and now the third one, well, I know it's C. In this particular, this is sort of a degenerate form of symmetry, but I think it probably, I don't know, there are people who are better qualified to say whether it qualifies technically as symmetry, but it qualifies in the following sense. It's a determinate point process. It just says, look, I'm going to pick a random place to put anything I get. And as long as it's different enough from anything else that I've seen so far, in this case, up to 3, I'm good. As long as those are discriminable, as long as my symbols are discriminable, I'm good. And that's sort of the way it solves it. Okay, so that works over any data, right? It's the most simple form of relation, which is identity. Is that something's the same or not, right? And everything else, it's just binary. This too, I think I'll have a word to say about at least sort of in a minute. So the argument is that with this architecture, we can learn abstract functions on the abstract side. The external memory gives us the capacity for variable binding. It's always been discussed as a form of binding, and now I'm just going to say, well, it's not just there for inference and remembering when you park your car, it's for variable binding. Like, so if you have a function and you need variables, you can bind the values of them. And that this gives us at least the form of a sort of simple form of symbolic computing. And it turns out this has pretty broad applicability. We've implemented it in the architecture I showed you. There's a distillation and abstraction of it that Giancarlo Kurg and Yoshua Bengio's group did, called the Corel net, which basically makes the observation that what the network is really doing, the LSTM is learning how to keep track of the items, in this case, the 3 items that are shown as the memoranda. And then once it's gotten them all, construct a similarity matrix, just correlate every one with every other one, or do a dot product, right? And then take that Corellogram, if you will, and then run that through an MLP to solve the task, right? And that turns out to work really well, in fact, better than the original model because it doesn't have the gradient loss of the LSTM, and it runs fast because you can run the whole thing feed forward. And for certain kinds of problems, it does really a good job. That's sort of at the simplified end, all the way out to work that our colleagues, John Lafferty and a student of his, Ani Altaba, have done, building this into a transformer. And I won't go into details there, but basically the insight is that if you separate out the keys and the values, the keys and the queries from the values. So you use the keys and the queries on the embedding side, but then retrieve values and then keep the values separate. And then basically transform the values. It's a form of symbol passing. And in fact, they write it down that way, and again, above my pay grade, but they have some proofs that this satisfies at least certain kinds of dicta for symbol processing. Then you've basically implemented in a transformer this relational bottleneck. Kamesh.
Just wanted to point out, this is pretty related to the question.
Yes.
When Dima brought up positional encodings and you add them to the tokens,
yeah,
this is keeping them separate and using them separate.
Exactly. And so keeping them separate allows them to be used as relational structure rather than just sort of munged up and conflated with the data itself. So there's a variety of architectures and variants thereof. Kamesh has been working on even more interesting versions that involve stacking of LSTMs to exploit the kind of things that that were talked about in the last talk, having to do with weight sharing, which is why I was asking the questions I was asking. So I think there's a lot of interesting directions. It's been applied to a variety of different tasks. I don't have time to go into it here. I'm getting tight. But things like visual reasoning tasks, sequential ordering tasks, prediction and planning tasks. These are all written up, and anybody who's interested, I can send you papers. And here is sort of, I think, maybe for me, the most interesting point. This all looks very machine learning and sort of computer scientific. But if we just rotate it a little bit, it looks a lot like the brain. So I said that I thought part of it may be implemented by the hippocampus, the binding part. But the separation, what about the separation? Well, if you think about the portal of entry to the hippocampus as parts of the medial temporal lobes, which we know have certain kinds of structure, like that's where the grid cells live. And you imagine that different parts of the neocortex project to different parts of the entorhinal cortex, the sort of portal into the binding mechanisms in the hippocampus, then you have that architecture. And so in this sense, I think it does sort of map on, and you can imagine that the abstract side is the part of the brain that has often been, associated with executive function and higher cognitive, competencies like the prefrontal cortex, and the posterior part of the neocortex doing the embedding and then, like motor control. And as long as they sort of project to somewhat dissociable areas in the entorhinal cortex, you would be implementing this architecture. It needn't be the hippocampus. That's the most famous area for episodic memory. I believe that there's another big swath of brain that hasn't been explored very much. But if you imagine that the hippocampus is really important for inference, for sort of where did I park my car today? Those are sort of encodings and embeddings that you're trying to associate with each other. But not so much with things like if I want to do this and this, how do I sort of know, or if I do this and then this to sequence movements, what part of the brain might you look for that? Well, maybe the cerebellum. And the cerebellum has many of the same properties as the hippocampus. It's a hell of a lot bigger than the hippocampus. It increasingly looks like it plays an absolutely critical function in cognitive functions. And I think a super interesting hypothesis is that the cerebellum is playing this role in the affordance or action domain that the hippocampus is playing in inference and categorization. And that's something we're just starting to think about and start to look at. Okay, of course, it's not as simple as this. Neither are there any one or two controllers in any one part of these brains, nor is the prefrontal cortex entirely isolated from posterior neocortex. And so I think really the program of research in terms of understanding how we can both elaborate these architectures for computational and theoretical reasons, but also think about how they're implemented in the brain, is to think about what the dial is that one turns on the interactivity between areas that are standard sort of deep learning sort of areas and their isolation with respect to the ability of one part of the system sort of be biased towards towards abstraction. And that seems to me a really interesting, you can think of it again as a hyperparameter that is super interesting to explore. And we've done a little bit of work on this. And indeed, when you relax that constraint, in particular, when you allow the abstract side to not see the data, but have the capacity to shape or modulate the data, you get really interesting properties that increase efficiency of learning sequences, for example. And we have a paper that's just coming out on that. If you're interested, write me and I'll be happy to send that to you. Okay. What are current directions? And I hope this will answer at least a few of the questions that were asked earlier. I'm not going to spend much time because I want to get to the second half of the talk. Most of the work so far has been on identity and, simple and ordinal relations, simple non-metric relations, and flat structure, non-hierarchical, non-recursive, things like language are much, richer. And so what about contrastive or metric relations and hierarchical or recursive structure? One, I think, super interesting project that Kamesh and Simon have been working on is whether we can get a network like this to learn base counting. And you can think about base counting as, in some sense, I don't know if it's the simplest, but it's certainly one of the most fundamental symmetry functions. Your ability to sort of add one up to some number, right? And then know to recurse, keep track of that, right? But then recurse and do it again and know what the relationship between the places that you've been keeping track of and your loops through that that sort of finite set of digits. And Simon uncovered a really interesting paper from about 20 years ago, doing a group theory analysis of the carry operation in arithmetic, and looking at that. I don't have the time to go into it, but it looks super interesting in terms of and why nobody's looked at this, I don't understand. It seems like such a fundamental and easy, well, seemingly easy question. It turns out it's not so easy. Kamesh is trying to build models that actually do this, and it turns out to be trickier than we had hoped. I think some of the ideas that have come from thinking about the problem this way, and the group theoretical analysis in particular, are leading to some really interesting hypotheses about the cognitive processes involved in base counting. So keep tuned for that. There's work going on in artificial grammars by our colleagues at Yale, John Lafferty, as I mentioned a few minutes ago, and its application to maze navigation. Matt Rosenberg here has gotten interested in how we can determine whether rats abstract their understanding of a maze the way Tolman imagined. It's been very hard to sort of pin that down. And we know that the hippocampus is involved. Nobody's ever proposed that this is the reason, but it seems like a really interesting hypothesis. And Matt has his fingers on the neurons themselves. And so there's a chance that we can actually start to test this out, not only through behavior and computation, but through actually looking at brain function. And then finally, there's some interesting information theoretic interpretations of this. We do have a paper that summarizes the relational bottleneck sort of as a principle and some of these implementations that I've mentioned. It's a paper first authored by Taylor Webb. It's on arXiv, it's under review, and we hope it'll come out soon. And it frames the problem actually in terms of the information bottleneck work that Bill has contributed, and thinks about it as sort of a version of the information bottleneck where you constrain the loss function to be about relations rather than just unconstrained sort of information. And there's another paper that is trying to relate that to hippocampal function and capacity constraints. Sorry, not hippocampal, to Hebbian learning in Hopfield nets as a model for episodic memory and capacity constraints and cognitive control. That's all I know, a lot of sort of hand waving, but I just don't have time to go into it. But all of these things are written out. So if anybody's interested, just let me know. Okay, so variable binding is great. Symbolic processing is great. It's super flexible. But it introduces a problem, the binding problem. If I bind X to 5 and I want it because I want to subtract it from 7, and now I say, oh, but wait, I want X to be 12 because I want to do a difference. That doesn't work, right? I have to sort of only do one set of operations at a time. I mean, in some sense, this is why the original traditional computers were symbolic. Once you bound the variables, you had to finish the computation before you bound them to anything else. You can't bind multiple numbers to X at the same time and get the right answer. That means you have to go serial. And this aligns with a very long tradition of work in psychology about control-dependent processing. For example, when you do a mental arithmetic, you do it serially, and it demands what psychologists will call control. If you're distracted, you fail at it, you're not very efficient at it. I'll say more about that in a moment. And so this distinction between control-dependent processing versus automatic processes, like, flipping this while I'm talking to you, or, I mean, all the things that my brain is doing in managing my body are being done sort of automatically. And of course, you have the capacity to go from one to the other, as I mentioned at the very beginning. I can go from doing like this to doing this, and this would be called automatic. In fact, by the time I do this, I don't even know what my fingers are doing anymore. When I do this, I know exactly where my finger is, right? So there's this sort of general sense that there's this distinction between controlled and automatic processing in psychology. And so I want to talk about that because I think it relates to this idea of self-configuration and provide some insights into how we can design systems that, leveraging all the things I've said so far and what we know from psychology, can be truly self-reconfiguring and, in that sense anyway, autonomous. Okay, so automatic processing, as I said, is typically thought of as being efficient. It's parallel, but it's rigid, right? If I learn how to touch type, it doesn't help me on a piano. If I learn how to play chords on a piano, it doesn't help me touch type. There's a little bit of transfer of using lots of fingers, but for the most part, very thin. And that's been a disappointment to psychology, like, in terms of the ability to understand what it takes to learn a skill and move it. Conversely, control-dependent processing is very flexible. I can do arithmetic over any set of numbers that I care to. But it's, as I mentioned, inefficient, it's slow and serial. And one of the central tenets about cognitive psychology for over 50 years has been the reason control-dependent processing is that it is like a central limited capacity processor, like a CPU, right? That it only has one set of registers. It can only do one set of variable binding at a time. And I'm coming around to that view, but not for the reasons that people thought. A lot of things were attributed to being control dependent because they seem to be serial when in fact they're not. And so I want to give you an example of that that's going to make a different point, which is that control isn't the problem. It's not that there's a CPU and it only has one set of registers. The control part of the system can do as many things as the system wishes, right? But rather, control seems to be capacity limited when you're doing something that uses shared representations, symbols being the prime example, right? And control is there to ensure that it's serial so that you don't screw up and get conflict due to dual use of the same set of symbols for different things at the same time. So the mistake that I think psychologists have made is blaming the fireman for the fire. The fireman is always there, but it's not, the fireman didn't cause the fire, right? Even though there's a correlation, it's not causation. The fireman is there to solve the problem, not having, it's not there, it's not the person that created it. So control is there to solve the problem that's needed to be solved when you need serial processing. It's not the constraint itself. So let's make this super concrete. I'm gonna ask you all to respond to a stimulus out loud as quickly as possible. If you're a psychologist, you have to shut your traps, as you'll know. But for anybody who's not, just respond out loud as quickly as possible. Thank you. Nobody said red. The psychologists were very polite. Right. So what happened here? You saw a stimulus. It has two dimensions, color and orthography. You all responded to orthography, and you did it quickly and demonstrably about 150 to 200 milliseconds faster than if I had asked you to name the color. And that is arguably the most robust phenomenon in all of psychology. In fact, you can't overcome it by the time you're an adult fluent reader of the language that's being done. There's one psychologist who's well known for having studied this in his entire career, Colin MacLeod at Toronto, and he was so convinced that that should be overcomable that he spent 20 years training himself on color naming the color. And after 20 years, he actually got it to be roughly unaffected by the word. But everybody else, not only do they take longer to name the color in this situation, but if you distract them, they can't do it. So what's going on here? Well, in a simple neural network version, you have two sources of input, the color and the word. There's processing along two pathways that converge on a common output, phonologic code for saying red or green, right? And if I just ask you to speak out loud, you go with the stronger pathway. Why? Well, you've had more training and more consistent mappings from these sorts of orthographic stimuli to these phonologic codes than these colors to these words, right? By the time you're an adult, you haven't spent a lot of time recently going, oh, look, mommy, red fire truck, right? Furthermore, red means lots of different things. You see red in lots of different contexts. But when you see this word, this is really the only phonologic code that goes with it, right? At least with regard to that particular stimulus. So it makes sense that you all said green. But of course, if I asked you to name the color, you could have. And that's perhaps one of the simplest examples of cognitive control, right? You have a representation in your head that says, look, this is what matters right now. How it got there, we won't talk about right this moment. Though I think what I talked about in the first part of the talk gives us some hints. And that primes or facilitates or gain modulates the processes here, the representations here, so that this can dominate the response, right? Now, without that, if I tried to ask you to do both, you'd say something like red or green. So you can't multitask this, but it's not because you don't have two units. I could turn on the word unit and the color unit, and I get a perfectly good orthographic representation and color representation. In fact, I know that's the case because if I do fMRI, I can see those both in your head when you're staring at the stimulus. But you're not going to allow both of them to be equally expressed, or you're going to get a big munge up here. So what's going on here is that you have a shared representation of your phonologic code. That's causing a risk of conflict, saying things like red or green. And so you have control here to keep you from that embarrassment, right? To do the appropriate thing. And you don't need it for green because you already have your history to help you with that. But if you have to overcome that history, well, then you have control, okay? So the purpose of control in this case is to prevent conflict. It's not that control could only do one thing at a time, which is the standard story. It's that control had to do this so that you didn't try and do two things at the same time that it would be stupid to try and do. Now, you might say, well, this is just an output problem. You only have one mouth. And if you only have one mouth, there's no point in having more than one phonologic code. Well, we're going to do a little demonstration to show you that it's not just an output problem, okay? All right, 3 tasks. First task is, it's going to be the Stroop task. This is called the Stroop test, by the way, for those who don't know. And this time you're going to do it through color name. So you're going to name the color of the stimulus that's going to appear on the screen, okay? It's going to appear on one side of the screen or the other. And I want you to point to the side of the screen that it appears on. Okay, so name the color. So if you see color the word blue in yellow ink, you have to say yellow. Okay. And then I want you to point at the same time. All right, everybody ready? Very good. Very good. Okay. So there you go. You just did multitasking on something that if it was just control dependent, color naming, you couldn't do. You just disproved 50 years of psychology. That it's possible to multitask a control dependent task because color naming is control dependent, right? As we just said. And yet you were able to do things at once. Second task. I'm going to show you a word now. It's going to again be a Stroop stimulus. I'm not showing you the colors here because I don't want to bias you, but in the middle of the screen this time, there'll be one of these Stroop stimuli. And this time, I want you to read the word, but don't say it out loud. Nothing out loud. Okay, no speaking this time. You're just going to point. And if the word is red, you point left. And if the word is green, you point right. Okay, everybody get it? Red, left, green, right. Okay, so a little bit of uncertainty. All right, this time much better. Okay, so now, brand new test. Never done that before. Pretty much one-shot learning. I'll show you data on this in a minute. Okay, last thing. We're going to combine that last test. We're going to do exactly the same last test, only this time, I want you to name the color of the stimulus. Okay. Yeah, I hear some groaning. That's an interesting fact unto itself, phenomenon to itself. You know that this is a different beast, right? That actually, we'll come back to that at the very end. All right, ready? Half the room is pointing one way, half the room is pointing the other, right? Just give it up. And anybody who got it right, I have the data to show that you didn't do it parallel the way you did the first one. So the way I know that is that when we do this in the laboratory and we constrain people to respond within the time it takes to do the slower of the two, but both have to be done in that time frame. So there's not time to sort of first do one and then sneak in the other, right? You can't time slice or serialize. You have to do them both at once. This is what it looks like. You can do the color naming location pointing, not perfectly because you're being forced to do it under duress, right? But 78%. This is hundreds in the lab and thousands online, by the way. You can learn the word pointing task almost immediately and almost to perfection. Nobody can do this. Not after 10 trials, not after 100 trials, not after 1,000 trials. After 10,000 trials, you can start to do it, right? Sort of like this, right? Versus this. Okay, so what's going on? So here's the color naming task. That's just our friend, the Stroop task, with a little added control unit that says I want a verbal response. Why? Because we're going to add another response in a moment. Okay, there's the other response manual. There's the location pointing test. So I see something that's on the left side of the screen or the right side of the screen. I have some representations in my parietal cortex that know about space, and I'm mapping them to something like my hand that knows about the parietal representations that know about space. So I have no problem doing that. I have no problem doing this because there's no conflicting information, right? They're two parallel pathways. And for the most part, the first approximation, you can do them both. Okay. Now I ask you to do word pointing. And for that, you have to learn a new representation. Now, are you going to learn new representations for orthography? Why? That's crazy, right? You know how to read words. So all you have to do is learn how to map those onto a manual response. And you can do it pretty damn quickly. But here's the rub. Now, I ask you to do this at the same time as this, and you can't. Why? Well, because to do color naming, I have to turn on this set of verbal responses. It's a naming response. And to do word pointing, I have to turn on this to read words, right? And the minute I turn this on and this on, I've got my friend word reading, which is dominant over color naming, and it screws you up. So you can't do them both at once, right? Why? Because there's a shared representation here, no longer an output problem. This is something you learned, right? And, you know, what's the evidence for that, right? Is that you could have done it this way. You could have created a whole new set of units, just allocated some new units that map from words to pointing, and it'd be parallel. But we know you didn't do that because you couldn't do the task. If you could have done it, you would have, I assume, right? And we know, as I said, from thousands of hours of subject training that this, you can learn to do this, but it's not what you learned first. And what's super cool is that we can do brain imaging studies where we show that when people first do the task, they do it this way. And with enough training, when they get good at it, after those 10,000 trials, then they look like this. We can see this separate in the scanner. It's provisional data, but it looks like that's what's going on. Okay, so what is this telling us? Here we had separated representations, no conflicts, we can get away with it, okay? And parallel processing. So this is, one could view as sort of the automatization of the process. So here's sort of a high-level metaphor for what is going on here. what happens when you have intersecting pathways, whether it's, neural pathways or trains or cars? You build overpasses if it's trains or cars, right? You keep the pathways distinct. You have separated representations. And that's great. It's super efficient. These things can flow. But it takes like lots of money and lots of time. Anybody who lives or has been down to Princeton in the past 15 years and watched what's happened, right? It used to be all intersections. And it took years before they started building overpasses. And there's still not one at Washington Road. And it's a horrible place to go at rush hour, right? Why? Well, because, to build these things, especially if you want some flexibility, they get really expensive and complicated. What's easier is to just do this. And that's the way Washington Road was, it still is, right? You just have an intersection, and it means that when you get here, you can go left, right, forward. It's very flexible. You don't have to worry about the routing, all this kind of crap, right? The problem with that is this, right? There's possibilities of collision. And so, this is faster, cheaper, and more flexible. This is more efficient, parallel, but at the expense of lots of effort to build. And so the argument is that the same thing is happening in the brain. Shared representations are flexible, and symbols are the ultimate example, right? But they pose the risk of conflict, processing bottleneck. Control serves to prevent such conflict, to manage the bottleneck. The serial constraint on processing, therefore, is the purpose of control, not a limitation. This sort of reverses the standard interpretation. Normally, people think of control as reflecting sort of a bound on rational processing. There's just a limit to how much sort of rational, like arithmetic you can do in your head at the same time. Really, it's a rational bound on processing. It's saying don't do more than one thing at a time because you're going to get in trouble by the very nature of the shared representations. Okay, so this exposes a fundamental trade-off. In this form, right? So this is an example where I have 3 input modalities, 3 output modalities, and I want to map for a given task an input modality to an output modality. And shared representations is the most efficient way of doing this. We used to call it sort of the minimal basis set. It's the minimal sort of representations you need to be able to do all 9 tasks. But we've sort of traded that out for the term compositional coding because it comports with a lot of literature in neuroscience on the flexibility of compositional coding versus what I'll refer to as conjunctive coding. But the point is that it involves shared representations, and it's general purpose. It's fast. So I come in here and I can go any place. It's like that intersection, right? I can map it to anything I want. And in fact, Jeff Dean seemed to see the virtue in this. These things, I'll show you in a few minutes, they're fast to learn, they're really flexible. And so this is where AI should go. Google Pathways, this is from their website, right? This is what we want to build. We want to build lots of neural networks that have lots of these shared representations and makes them super flexible. There's a pathway, a single model that can generalize across millions of tasks. Woohoo, right? Multitask learning is a phrase that's used for this. It gives, lots of multitask capability, but what they're not thinking about is this, multitasking, that is concurrent parallel processing. If you built a system like that, it'll do lots and lots of things, but only one at a time. It would be as if you could not chew gum and walk at the same time. If the whole architecture was that, you're screwed. So, this is constrained. It can't be multitaskable. If you do these 2 things at once, you run into exactly the same problem I pointed out, that you pointed out in the word pointing and color naming task. And, I'd say, well, okay, maybe that's just one example that a clever cognitive psychologist sort of picked to make a point, but the brain is really big and there's lots of room for sharing and there's always a way around it. So we've done some formal analyses. I don't have time to go into this at all. We started with some graph theoretical analyses. There's some statistical mechanical tools that have been used to look at those graphs. And the bottom line is this. It's remarkable how constraining sharing of representations is, even in humongous architectures. It doesn't scale sublinearly. In fact, it hits a wall, right? So no matter how big the network is, based on certain assumptions, you end up with double, and in some cases, single-digit constraints on how many processes can be done at the same time when you introduce only modest amounts of sharing, like 20% overlap in pathways. Right? And that's a number that we picked because it turns out if you look at the Human Connectomics project and you ask what's the graph structure of the human brain, is the best they can infer from things like tensor diffusion mapping and connect pathways and connectomics at the macro scale, not the sort of synaptic scale. There's about 20% out degree. Or 20% sharing. Like if you look at the out degree and in degree on the graph, it ends up being about 20% sharing. And here's the plot. And this is representative of this analysis. This is a paper that was done by Giovanni Petri and a couple of other colleagues that was published in Nature Physics. And it shows that there's just a dramatic drop the minute you introduce any kind of sharing in networks, irrespective of scale. Okay, so it's a serious problem for network architecture, and Jeff Dean is not going to get away with it if he wants his agents to do more than one thing at a time. Okay, and so this is efficient. Multitasking is possible, and this is what you need if you're going to do multitasking. And just to show you sort of a dynamical simulation, maybe 3 or 4 more minutes. Oh, that's fine. Okay, I'm good. So this is a simulation that we ran that shows what happens when you train a network just on single tasks. You don't force it to multitask. You train it on single tasks, and then you ask, how well does it do at multitasking? It does horribly, but what does it learn? It learns these low-dimensional minimal basis set or compositional code. So what you, it's hard to see here. I don't know how well it's showing on the screen, but these different circles are the sort of eigenvectors that are learned using PCA. So eigenvectors from the PCA analysis of the hidden layer that sort of shows what are the components that the network learns. And there's 9 tasks that it's trained on, but it's separated them down into 3 sets, each of which is one set of encodings of the inputs that it then uses for the other tasks. So what this shows is that if you just train on single tasks, networks really prefer these low dimensional representations. That's why Jeff Dean was so excited by them. What happens if you train it on multitasking? So that's what we're doing here. We're training it to do not just single tasks, but also forcing it to do multitasking. And what it does is it first learns the simpler representation, the single task the minimum basis set. So you can see the 3 circles emerge. And then eventually, in order to solve the multitasking cases, it has to separate them out into 9. So this is evidence that in these sorts of networks, if they're forced to do multitasking, they still have a bias towards single tasking, but eventually they take up. So when you, that's like you going to play the piano, you know, using a single finger before you try and learn to play chords. And this paper by, this paper by Pyle et al. Is actually an analysis using neural tangent kernel analysis to sort of predict that this is what you would expect from at least a standard loss function in a backprop net. So, okay, so sort of step back and summarize. There's a trade-off between flexibility versus efficiency. Novel performance favors shared representations. They're faster to acquire, they're more flexible, but it comes at the cost of serial processing. This explains the capacity constraints of cognitive control. If you need to go parallel, you can learn to separate representations, become more parallel, more efficient, more automatic. This trajectory from controlled to automatic processing aligns with exactly what we've known about for decades in cognitive psychology, though now it provides sort of a quantitative underpinning of this. In many ways, you can think about this as something that computer scientists have discovered in their systems, interpreted versus compiled procedures. You know, it's simpler to work with an interpreter. It's more general purpose, it's more flexible, but of course, it's less efficient. So when you need efficiency, you have to compile the code, but now it becomes rigid, right? More broadly, this defines a strategic imperitemporal choice that an agent that has a choice over, that has control over which of these things to do, which it should do. Should it value the immediate value? Should it value sort of the immediate rewards of relying on control to do things quickly, learning how to do it quickly, but really inefficiently, you know, finger hunt and pecking, or put the time and effort in to learning how to become automatic. And so we've begun to, so I gave this example already. We've done some, oh, right. So this is a question about self-reconfiguration. Which would I rather be? Which kind of thing, which should I rely on general purpose algorithms for, and which should I sort of compile down and make myself efficient about? And we've done some analyses of this, at least in simple systems, starting with sort of simple networks. We've done some Bayesian sort of abstracted these and turned this into sort of a Bayesian optimization problem, at least in the context of reinforcement learning. And then we have some deep learning examples, and recently some information theoretical analysis of fairly complex nets to sort of formalize this and ask, you know, whether we can gain some insights into what the trade-offs are and what the parameters are that favor one versus the other in the environments that interact with those parameters. So that's about it. Big picture, you know, we have symbolic computing on one hand, neural networks on the other, you know, flexibility versus sort of function approximation, efficiency and rigidity. I've argued for an architecture that can sort of support both. It has the capacity for symbolic computing, but it also has the capacity to sort of reconfigure itself, to basically compile itself down for the things that it needs to do efficiently. And I think if we start to sort of exploit this, we'll gain some insights. about cognitively informed agent-based models, provides a path towards at least certain forms of explainable AI, autonomous artificial agents in this sense of reconfiguration, being able to build devices that can go out into the field, use their general purpose abilities for flexibility, but decide when they confront something that really needs to be mastered to go and do it, and then maybe even more humane human-machine interactions. So, we'd like to go somewhere like this to something more like this. And with that, I will put up acknowledgements of the people who have inspired me, the people who have funded me, and all the people who have actually made the work doable, fun, and productive. And then, as I said, some of them are in the room here. So thank you.
Hi, everyone, and welcome back to our afternoon session of the symposium. It is my pleasure to introduce the next speaker, Erik van den Eyden. Erik is a professor at Cohen Institute of New York University, and he is an expert in mathematical and computational aspects of statistical mechanics, with applications in a variety of fields ranging from molecular dynamics to material science, and also mathematical foundations of machine learning, which will be the topic of today's talk, in particular regarding generative modeling with flows and diffusions. Thank you, Erik, and floor is yours.
Thank you very much. Thank you for this introduction. It's a pleasure to be here. So I'll be discussing stochastic interpolant for generative modelings. As you can see from the first slide, there will be some overlap with the first talk this morning. So it's actually great that Dimas spoke before me. There's a couple of things that I will not need to introduce due to that. And the reason why it's zoomed out is because as soon as I will zoom in, the most important part of this slide will disappear, namely the name of the people who did the work. Michael Albergo, Nick Boffey, and more recently, Mike Goldstein, who are a student and postdoc at NYU at the Cohen at the Center for Data Science. Okay, now I think I can zoom in. Hold on. Like this. Right. Okay, so as I said, there will be some commonality here with the talk of Dima, but there will be the viewpoint that is being taken is slightly different. Namely, the problem that we're going to be considering is a problem of density estimation, which has emerged in recent years as one way to do unsupervised learning that has proved very successful. Okay, and so from a mathematical standpoint, you can think about it this way: you're giving data, so that's input data, the xi that are there, and you assume that they are coming from an unknown probability density. Okay, more generally a probability measure, but we're going to work with density. And what you'd like to do is somehow to estimate this density in such a way that it allows you to structure the data in a certain way, and maybe also be able to generate new data from this density. That's the part of the generative modeling, okay? And it's unsupervised learning in the sense that you only have inputs, but you have no label a priori. If you are given label, it facilitates the task, but it's not necessary. Now, this is the generic problem in density estimation. The reason why it has caught a lot of attention recently is because of this diffusion model. So these are two pictures that come from the paper of Yang Song and Stefano Herman, ICLEAR 2021, which started this craze into implementing this in for example, OpenAI in DALL-E, right? And the image that you see there are actually fake celebrities. So it's you train the data that you give, the XI are just pixelized, photographs of what's called celeb A, which is this data set that contains photographs of celebrities. And once you have trained that, you can. Yes.
There are people complaining they can't hear.
I understand that. So, okay, let me do that. So once you have trained it, you cannot generate new images, and that's the typical image that come out, and they look fairly reasonable. Okay. Now, it's a fairly old problem, obviously. The scalar density estimation that we use, and so on and so forth. I list a few methods here, but there's been recently
really a revolution in a way by introducing this normalizing flow and more importantly, these diffusions, which with the conjunction of having a lot of data available and the computational power and expressivity of neural network has led to the advances that I just, these images. And, DALI does many more things because you can actually prompt, they are integrating large language models, so you can have a text prompt that create image and do these amazing things. Okay. So the method that I will be discussing here are based on dynamical maps on flows. So this also connects with what Dima was discussing this morning. And so the basic idea here is that we're going to try to construct an ODE or an SDE, so an ordinary differential equation or a stochastic differential equation, which has the following property, which is that if you feed it an initial condition from a simple density, say a Gaussian noise, say, then if you pass it through, you simulate this SDE on a finite amount of time, what it produces is a sample of the target density you're interested in. Okay, and there's a little illustration here that tells you what, how does that work. So you train your network, will explain later in the talk how that's done, obviously, but you train the network, and then what it does is that it takes an image which is pure noise, so every pixel is just drawn at random. That's what this white noise image that you do, and then you take that as an initial condition for this dynamical system, you push it through, and it produces an image, okay? And so this is not only interesting for generative modeling, it's also interesting for sampling. I'm mostly interested actually in problem from scientific computing where you need to sample distribution, for example, in Bayesian inference or in statistical mechanics, in which case that's a way in which if you can sample easily from the base, again, the Gaussian is easy to sample. If you have such a map, then you can create a priori sample from arbitrary complicated distribution, which would be useful. Okay. And so, of course, the question is, how do you find the velocity field and possibly the diffusion coefficient that you need in an equation like that to do the task? Okay. And I'm going to rely on, there's a lot of mathematical result on this, which is related to transportation theory, optimal or not, that guarantees existence of these velocity fields in certain cases. But what we would like to do here is to find constructive ways to estimate them, okay? And by that, what I mean is to be able to frame it in a shape which is such that the problem becomes amenable to deep learning. And for me, what that means essentially is that the velocity field that you are trying to find needs to be the minimizer of an objective function, a loss, if you wish, which is such that if you then parameterize the velocity field with a deep neural network, a transformer, say, then you can just optimize this objective function to find what are the parameters. And so you need two things for that. You need to have that there is one such objective function, and also that you can estimate it. So you can empirically estimate it on the data. Right? It's not something which is abstract, which involves big integrals that you would not be able to do. You want to have something which you can estimate on the data. And I'll try to explain how this can be done. Okay. So what I will do now is essentially three parts. First, I'll discuss what we have done in the topic, which is the stochastic interpolants. And there's a few other groups that have done things similar. Then I will try to connect that to existing method that you might know or be interested in, like diffusion, the original framework of Song and Ehrman, and then other things that involve denoisers, which I think that they've been used in computational vision for quite a long time. And then, time permitting, at the last part of the talk, I will give an application that's from physics, which is active matter, is to try to quantify or the non-equilibrium nature of an active matter system that I will introduce. Okay. So for the first part, let me just go through a few, there's a few definitions that we need to have. I'll explain to you, or try to explain to you, how you can build a connection between samples from the base and the target density, assuming that you have them, and then do that in such a way that it allows for, in principle, easy estimation of the velocity field that transport these samples. So the way it's done is that you introduce this x of t. I'm not really sure how to point on the screen, so I'll just talk and you'll figure out which equation I'm referring to. But so this x of t, you construct it as being a linear combination, time-dependent linear combination of a sample from the base density, the simple one, which will be denoted by x0, a sample from the target, which we denote by x1, and then we, for reason that will maybe become clear later, we're going to add a latent variable to that, which can be tuned. So this x0 is the base, x1 is a sample from the target, and z is just a Gaussian, which is a latent variable that is added. Okay, and so the x0 and x1 could be correlated. Z is independent, and then you have these coefficient alpha, beta, and gamma of t, which essentially are differentiable function of time that are constructed in such a way that at time t equals 0, this process is a sample of x0, and at time t equals 1 is a sample of x1. So at time t equals 0 is a sample from the base, and at time t equals 1 is a sample from the target. So in this way, they interpolate between the two density. And in order to do that, you just have to have the boundary condition that are at the bottom of the little box. Okay. So for example, you could take alpha t equal 1 minus t and beta t equal t. You could take gamma equals 0 if you want. And then you see that at t equal 0, alpha is 1, beta equals 0, and the other way on the other side. Okay. And you could imagine that you sample the sample from the base and the target independently using just a product measure. Okay. And so if you do that, you see that, well, by definition, the process goes from the base to the target. There's a little picture here that illustrates what it does. It doesn't need to go from a Gaussian necessarily to the target that you have. It can go from any density to any other. So this cloud of point is just what happens if you pass them. So the one that you see that is these two moons are, say, the sample from x0, and the one that are on the checkerboard are sample from x1. And if you interpolate them with the linear interpolant that I've written on the slide, you get the cloud of point move that way. Okay, so you're creating sort of a connection in density space between these two objects through the samples. Okay. It doesn't go from first, it doesn't go from the target to itself. It could, but that's not what's done. It goes from something simple, like a Gaussian, to the complicated target. Okay? And so, and the idea is that we're going to use that. It's a way by which you can take this simple Gaussian density and turn it into something which is more complicated. And we're going to learn what it does. That's in essence. So, okay. If you bear with me for a few more slides, I hope it's going to become clear. Okay. So the other cloud, yes. Yeah, you can pair them all. Yeah. That's right. That's right. Yes. Is that? Yeah. So there is no pairing here. You're not using a predefined map. It's independent sampling. And so when you create the process, you pick at random, a sample from row 1, a sample from row 0, and you just draw a line in between. And you do that for all of them. Okay. So at the level of this process is actually pretty nasty because it goes, but it moves the density in a nice way. And we can represent this motion in a nice way. So that's what I'm going to try to explain. Okay, and that's the okay. So this is just using flowers, where here is connection from the data set to itself that show again what happened in the previous slide. I showed you what happened if you look at the full density as it moves. This is showing you what happened to one single sample as it is mapped into another sample by this linear interpolation. Okay, so the first one is something where there is no latent variable, so it's just linear interpolation between the two. And then there's other things where you can dissolve it into more noise in the middle if you want or not. Okay. So what's the key to understand what's going on is that you, instead of looking at what the sample do, what we're going to do is we're going to look at what their probability density do as a function of time. And we'll find out that it satisfies a transport equation. And then once we have this transport equation, we'll be able to sample it in other ways than the one that we started from. So bear with me, I'll explain that. So the first thing is that here is a transport equation. You can, so if you look at the probability density of this process, so it's something that depends on time, right? It's the probability density of the red cloud that you see on my first slide. It satisfies a continuity equation, which is written there, right? With the right boundary condition by construction, because the samples start from ρ0 and go to ρ1, and with a velocity field that can be expressed as a conditional expectation of the time derivative of the interpolant condition on observing it at a given point. Okay, so it's really like, you have all of these paths that do something which is quite complicated. You look at the point, you fix yourself in space, and you ask what is the average velocity that they have over there, and you define that the velocity, that's what moves the density, not surprisingly. Okay? And interestingly, you can write down an objective function for this velocity, which is just quadratic regression. And that's the one that is at the bottom of the box. Okay? And so the velocity field that appears there is something that minimizes over all velocity field in a certain class this quadratic objective function in B hat that they've written at the bottom of the slides. Okay? So the unique minimizer of that is the velocity field you are looking for. And this is a tractable objective because it involves only expectation with respect to the stochastic interpolant that you have defined at the beginning. So if you have sample from the base and the target, you have sample from xt, the interpolant, at any time, and you can use them to replace the expectation in this objective function by an empirical average over the samples. Okay? And then we're going to discuss that maybe later, but if you know replace this velocity field by a neural network, say a transformer, then you can optimize over the parameter of the transformer. Okay, we'll look at that in a little bit. So the difference maybe with respect to what Dima was saying this morning is that it's not something which is sequential, where you would learn blocks. You're really learning a velocity field of space and time using this big machine, and then you're going to use that later. Okay, and if you want to derive these equations, actually elementary math is just you take the, well, it's chain rule based on the definition of what the density is. That's the last line. That's not very important. Okay. Okay, so and to get the variational formulation, you just use the property of the conditional expectation, all this. So that's what I already just said, right? Is that it's tractable because, at least in principle, because you can parameterize it and optimize it. So you can estimate it, parameterize it, and then do the optimization using stochastic gradient descent or any. You can use all the toolbox of modern machine learning. Okay. Now, there is a corollary to this, which is that this transport equation can be solved by the method of characteristics. So you can write down an ODE, which is just the ODD that transport the samples. So this ODE is the one that is written in the box below. And that ODE uses the velocity field now to push sample from the base to sample from the target. So that, what does that mean? That means that the solution of this ODE have the same law as the stochastic interpolant that you had at the beginning, except that the stochastic interpolant is not very useful as a generative model, because to do the stochastic interpolant, I need sample from the base and the target. But once I have learned the velocity, then you can use it in the ODE, and the ODE just go one way. You can take a sample from ρ0, know the base, and then push it through that and get a sample from the target. I think I have a little picture that explains this, right? And which I also, I think this maybe clarifies something that we discussed with Bill a moment ago. So here's what's happening if you have a ρ0 that's a Gaussian, that is being pushed forward into a ρ1 that is a Gaussian mixture with three modes. So the original interpolant that you would have here would take sample from one of the distributions, so the Gaussian, and sample from the other one, and draw lines in between. So since we are in 1D here, all these lines would cross in a terrible mess, okay? But if you look at what the density is actually doing, the density is doing something which is fairly nice. And then if you look at what the velocity field that you learn is doing, it's doing also something which is very nice. In particular, at the level of the ODE, there is no more path crossing by monotonicity in 1D. So they all, so what you see here, these white lines are just, you know, it's how a sample taken from row 0 would be pushed onto one sample from row 1, right? And it also shows that in this picture, you can sample row 0. You need to sample row 0 to sample row 1. Every initial condition is mapped into one final condition. By doing the sampling at one end, you get the sample at the other end. Okay, I'll get to that more in a minute. Okay, since you have the method of characteristics, that's kind of useful. You can calculate likelihood and things like that of your. So, for example, you can estimate the quality of the map that you have constructed. Maybe that's not super important. And maybe I have already said that, but let me repeat it. That's the box that's at the right of the figure. We have created a process that has the same law at every time than the stochastic interpolant, but that one that is usable, unlike the stochastic interpolant. Because to use it, you only need sample from one end instead of both. Okay. Now, there's another thing that you can do, which is will later be related to the connection between this and denoiser, which is that you can also use the same trick to learn what's called the score, because the Fisher score, which is the gradient of the logarithm of the density. And there is just an estimate. That's why we added the latent variable. There's an estimator that gives you what is this score. Okay, the gradient of the log of the so that's the one that in diffusion, for example, they use, and this is a consequence of Stein identity. And so that's interesting because that means that now you can do something else, which is that instead of only using an ODE, you can also use SDE, stochastic differential equation, to do the sampling, because you can use the score to turn your transport equation, which is the first equation in the bottom box, into Fokker-Planck equation that go either forward or backward in time. And the reason, or you can do that, is you add a diffusion term in the right-hand side of your equation, and then you compensate it using the score on the other side. And so all these equations are in fact written exactly the same. They're just rewriting by using identity with the score. Okay? And so now that means that you have generative models in which you can push your sample through ODEs or through SDEs. There's a big flexibility, and you can go one way or the other, and you can go from an arbitrary base to an arbitrary target. Let me try to explain that maybe with this little graph. This is we're going to do into higher D later, but so this is what happened if you go from the top graph is what happened if you go from mixture of 2 Gaussian to a mixture of 3 Gaussian in 1D. And then the 3 rows that you see are just different choice of interpolant, like the way you construct the connection at the beginning, okay? And depending on what you do, you can either eliminate the structure by turning all the data into noise and then turning it into data on the other side again, or you can keep the structure. And once you have done that, you can now learn the velocity field and the score, and then you can sample these probability density function as a function of time by pushing the sample through the ODE or the SDE. So on the bottom figure, you have the 3 rows. So what you see, the 3 columns are just the same density. So it's the same connection because it was the same interpolant. It's just that now what you use to sample them is either an ODE or an SDE with various level of noise. And by construction, all of these, if you learn the velocity field and the score exactly, they all do unbiased sampling of one distribution given the other. Okay? Yeah. Do you mean at the level of the density? So the latent variable that is being added is precisely to guarantee that you will have a velocity field that is smooth enough. Okay, you can guarantee that it has, it's differentiable to a certain order. Now, if you're asking, can we control what would be, for example, the Lipschitz constant of this velocity field a priori, that's much more complicated because that depends on the structure of the density in high dimension that you're interpolating. And we have very little result about these kind of things. Typically, when the mathematical result that we have are pretty pessimistic, and the bound that you get tells you it should not work in practice, even though it does. So, okay. Okay, so here is one first example of thing that we can do with this, which is, so this is creating a flower. So it's training on a data set, this flower data set. And then it's using what you see here for all the columns is using the same noise. You draw a noise, and then you pass it through the interpolant with different level of noise in the SDE. So the first column, there is no noise. So if you were to repeat it, you would always get the same flower. And then if you go down, it's like each time 2 rows is the same noise passed to the SDE, and then you realize that it creates diversity. From the same noise, we create multiple flowers. Okay? And also connected to a comment that was, by Dima this morning, there's something which is, to me, completely magical that is happening here, like which and I'll elaborate upon that a little bit more later, which is that you generate images that are not in the data set. And that's completely, to me, flabbergasting that you don't memorize. Like, for example, you see that the flower at the bottom there that's standing alone, that's the flower that has been generated. So you can go to the data set and ask, what's the flower in the data set that is the closest to it? And the 5 flowers that are the closest to it are the ones that are shown below. Okay? And interestingly, if you ask, that's more like for the second talk this morning, all of these flowers have, in a way, some feature in common with the one that were generated. So if you ask people, they will typically find that one of them is closer than the other, but they don't agree with one another. So it is like, but it's a different flower. Okay. Yeah. So it's, I mean, I will, if you bear with me a little bit, I'll go back to that later. It has to do with implicit regularization, probably, of the neural network. Because we know, in fact, for these examples, we can compute by hand exactly the solution that would overfit the data. There's an explicit solution. And that is not the one that is being found by the neural network, in the sense that the neural network finds a solution that is implicitly regularized in a way which we don't understand, but that's a little bit like with all these neural networks, that does something which is more elaborate than memorization. In this example, right, what you do is that you use the data set to create, to learn the velocity field, but afterwards is by definition out of sample generation, because you use the velocity field that you have learned, you give it noise and you push it through and you see what happens. Okay, so at the generation stage, there is no information anymore about the training data set except for what has been encoded in the velocity field that you have learned. For this one, I think it's a transformer. It's something which is that we can train on one of the GPUs. So it's something small compared to what is being used, by OpenAI in DALI. It's like baby. You would be able to do it. There's nothing very special here. I think we moved to transformer after a while, but you could, any reasonably expressive neural network would do here. Okay. It's also, there's something which is important here, and that maybe is, related also to what Dima was saying, is that you're not learning a map. For people that do dynamical systems, the comment I'm going to make is very obvious. You're not learning the map. You're learning the velocity field underlying this map. And so you can have simple velocity field, obviously, that create very complicated map. That means that at the level of the velocity field, the expressivity might be less than what you need for a map. Think Lorentz 63. The velocity field is very simple, but what it creates is pretty complicated. Okay. It's difficult to quantify these things, obviously, right? Yes, it does. So it's essential. So it is, unlike in the talk this morning, we want all the action to happen in time t 0 to 1. So it's not a dynamical system. This is not ergodic sampling. Is you take sample, you push them for t equal 1, and you want to have that at that time. There is no concept of running them longer to get better result. In fact, that would create things that are worse. To do that, you need a velocity field that depends on time. However, you can show that this velocity field can always be expressed as gradient field. They would be time-dependent gradient. And that's simple result from transportation theory. So we don't do that. We don't learn them as gradient because a priori don't need that. It would be important the velocity field be a gradient if you want to, for example, to sample it so that you can guarantee that that there's a minimum. But since everything is happening in finite time, the structure that is gradient is not that important, it seems in practice. And if you use a neural network to model the velocity field as the gradient of a scalar field, you lose expressivity. So we don't do that. Okay. And also the transformer architecture typically is better to go from same dimension input output. And so here's another set of example, which shows you that you can do things where you do a correlation of the data. So this is what's done here is kind of, so it's actually simple. The column which is at the rightmost column is an image in high resolution. So you take this image and you simply coarsen it on a low resolution. So you go from 256 to 64, okay? And just give me 1 second. And then you use this connection between the image to actually build a neural network that will be able to take a coarse image and give you one that is, again, at high resolution. So in this case, right, you can do them on image that were in the data set or not and test what happened. So you see here that, well, it takes the image and reproduce the, it's super resolution. So it kind of denoise the data, if you wish, reproduce the sharp feature. Yeah, you had, Dima, you had a. We could. Yes. No, we don't impose that. I mean, it's not completely obvious, except for the fact that in one case you have a scalar function, and in the other case you have a vectorial function with the output dimension is the same as the input dimension. It's a much bigger object, right? Exactly, yes. So from viewpoint of transport, what it says is that the way you move the samples is affected by whether the velocity field is a gradient or not, but the density is the same. In other words, you can move sample in a density without changing the density itself. So you can remove that if you wish, and what this amounts to is to turn the velocity field into a gradient, and there's a unique procedure to do that. It eliminates all rotation if you wish. In practice, it doesn't matter a priori, okay? No, I don't think it's a gradient. We didn't test it. It's actually pretty difficult to test. I don't think, it really doesn't matter because it's finite time, but it really doesn't matter. So it's not, you should not think about this as a dynamical system, which is, since it's not gradient, you can get chaos and things like that. It's trying to do something in a finite time. Right? There is no chaos on t equal 1. I mean, so the way the image, I mean, it was apparent, the way the image are being created, but this is not a statement necessarily about the dynamical system, it's more a statement about this manifold of images, which is that at least if you look at them by eye, you realize that very quickly out of the noise start to appear a structure that you would recognize, and then it just sharpens. So it looks like there is a structure in there, which is that the data, this is with respect to the talk we had, right, which is that even though this data is seemingly in high dimension, and where extrapolation or interpolation would be quite difficult, there is obviously something low dimensional into this data set. It's just that we don't know what it is. It's actually difficult to tell even if you have the network, but it seems that the network learns it. Yeah, okay. I mean, I think that what is very valuable, would be to try to have architecture that are as sparse as possible, because the training of these things is actually pretty costly. And I mean, the result that we have here are reasonable, but obviously they are nothing compared to what OpenAI can do with DALL-E, except that they are doing training that we cannot afford, because the number of GPU that they use is not something that any university these days can afford. Maybe they will, but it's really, they are costly, these things. Okay, so there was another question.
So you're starting from some Gaussian, let's say, in some dimension, you map it into the completely distributed plot.
Not in this case, right? No, not in this case.
But some typical, so there's some dimensional structure with the flowers. Do you get different results if you have if you're drawing a Gaussian in different dimensions? Do you know that?
So you can adjust in this framework. You could try to do some optimization over the base. Some of them, for example, are obvious, which is that if you think about this distribution have variances. So when you start with the Gaussian, you better start with a Gaussian that has more or less the same variance as the one even though the distribution you want to go to is not a Gaussian. The scale should be the same, otherwise your velocity field will have. So this kind of thing you can do, and you can either do it a priori just by processing a little bit your data, checking what is the variance, or you could do it automatically. Okay, so right. The dimension needs to be the same. So in other words, if you want to have maps that are invertible, you cannot go from a measure that would be singular to a measure that would be singular on another set, or even from a density to a measure that's singular, because otherwise you always need to have velocity fields that are singular.
Same dimensionality as vector space flowers.
Exactly, yes. It's pixel space. Pixel space. Okay, so this figure is the same, so I'm going to go quickly on this one. I think there's even maybe a movie, right? The movie is actually what happened along the flow. So same thing as Dima is. This example is different. It's the same, I think, same setup. You take images and then you put random masks. The mask can be random, and then you are simply learning how to use the masked input to get an image back. Okay, and the framework is sufficiently flexible that there's a lot of things that we know about the velocity field that we can put in the network. For example, we know that it should not, if you know where the masks are, which is, think about using this for editing, you know that the velocity field should not do anything outside these masks. So you can do that, zero it there and just make it appear over there. And this is another illustration of something that I find completely remarkable, which is, so these models generate images where if you use the SDE, for example, or if you draw different noise in the mask, you're going to get different images. It's a generative model, okay? And so the image on the right is the dog that we started from. And so this image is a little bit, again, like what, example that Dima showed, which is that the image that is being reconstructed is the dog with the eyes closed. And that's totally remarkable because, okay, if you don't, I mean, if you just look at it, you say, well, it's obvious that, it didn't know that the eyes was open or closed since it's masked. But then if you ask yourself, where the heck did he find the information to actually do that in a way which is consistent, which is that it really, if you look closely, the eye looks a little bit too flat. I mean, it's not perfect, but it's pretty damn good, including the eyelid and everything that is there, okay? No. Here they are similar. In this case, they are. You don't have to. In this case, you're pairing the data, which is that in the training, each time you give a masked image, and then you interpolate it towards its unmasked image. And you do that for all possible masks. And then you do a learning of the velocity that's conditioning on the masks, right? So the data are paired. But then when you use it, you remove all this information. You just give it a masked image, and you ask what is it? No, this is I mean, here the Bayes distribution would be the training samples of the Bayes distribution would be like the masked dog. Okay. So in this example, the only generation that you can do in terms of generative model is that you can take this masked dog and change the noise in the masks. And if you do that, you get different eyes, for example. Yes. No, that's what's interesting, is that even if you do, even if you train from noise in the, like in the flower case, right, there is sort of structure that is appearing, but not with the noise, right? If you change a little bit the noise, then it doesn't go very far from the previous one. And why this is happening again is a bit of a mystery. I really don't know. I mean, I don't know. It's property of the flow, it's a property of the data. The reason why I say that I'm completely flabbergasted is maybe it's a generational thing. Like younger people in the room might not be like that. But I used to do scientific computing, right, for my field, where we were saying any problem above 3 dimensions, forget about it, because there's a curse of dimension, you will not be able to do anything. And now we're doing things like this. We see that, these are millions of dimensions, and I feel a little bit like it's like living through the first plane, or being born after it has flown. For me, this is like, but we don't understand. I mean, the bottom line is that we don't understand, I think, and nobody really does. There's been like a breakthrough. There's a barrier that's gone, but we don't really understand. There must be low dimensional structure, otherwise the curse of dimensionality is there. They're unbeatable. So, but we don't exactly know what they are. That's a very interesting topic, but it's not. I will have very little to say about this today. Okay, so now I'm just going to make quickly connection with 2 methods that perhaps I think that might be interesting. The first one is in fact the one that inspired this whole work, which is the diffusion. Okay, the one of Yang-Sang. So what they did is actually, the picture which is here is in fact a picture from the blog of Yang-Sang. Is that what they did is that they thought about doing the following thing: is you take your data or your images and then you pass them to, you turn them into noise in a way which involves a stochastic differential equation, an Ocean-Beck process. Okay, I'll write the formula before. And then they noticed that if you can go one way, you can go the other way if you learn the score. That's a little formula which says that if you have a Markov process in one direction, you have a Markov process in the other direction, and you can write down what is this reverse. And it's not anti-diffusion, it's just going the other way, right? It's not anti-diffusion because the drift and all that is very structured. You need to know what is the probability, the score of the probability density to do that, right? And so that's what they did. And the major advance that there was here, which is the one that we also rely upon, is that if you do that, you turn the problem into a regression problem, which is that you can use the data to learn the score at any given time, instead of trying to use a maximum likelihood training through neural ODE, where in the training you need to do multiple passes through your network. That kills you. It's not doable with the big architecture. It's not tractable. This is, you first do the connection in probability space, and then you say, this connection give me this drift, and you learn the drift without having to go back and forth. That was really the breakthrough, I think, that that they had. Do you see that? In fact, it's because on my screen I don't see it, but yeah, it's actually, I see that I need to say a few things that in fact are written on the screen, but they are just below the little black bar, so you can't see them. Okay, so that's why let me repeat them. you build the connection in the probability space and that reduce it to a regression on the score. Now, so let me explain a little bit in the detail what's actually done, right? Is that you take your data and you pass it through a Notion-back process. So I don't know, I mean, this is an elementary SDE, is the one that is written at the top there, and you can solve it explicitly. And in law, the solution, what it does essentially is that at time t, the solution of this thing takes the initial data, which is your image, squishes amplitude exponentially fast, that's the e to the minus tau, and then add noise to it. And so it kind of take the image, remove all the features from it exponentially fast, and put noise instead. Okay, and that means that if you give yourself a data point, which is an image that like the dog, you can actually sample all of the snapshots afterwards very cheaply because it's just dimming the image and adding noise. Okay, and you use that to do regression, right? Now you realize that there's a couple of things here that are a little bit annoying with this, which is that first, this happens in infinite time. You cannot do it on 0, 1. Here you're relying on the ergodicity of the process to go towards this infinite measure, which in this case is the Gaussian. And if you want to change that, it's actually pretty difficult because then it's not going to go fast, etc. Second, so that means that you need to take t to be long. But second, there's another problem here is that the target is always the same. It's a Gaussian. It's only noise. You cannot easily go from a structured distribution to another structured distribution because there's no SDE that allows you to do that. Okay, but you realize that in fact both of these problems can be eliminated because there's a simple change of variable that you can do, which is you change the time. So you take t to be e to the minus tau. You rewrite what the process was. And you realize that, in fact, it is an interpolant. Like it's just a special case of what we are using, which does the job in finite time, okay, and then can be used to learn differently and to sample differently. So this is not meant as a criticism. It's just like, I mean, that when the score-based diffusion, there was really a conceptual advance that was major because they turned this problem into a regression problem, and that was really key to make it work. But there was one aspect maybe that was not realized, is that they mixed up two things, which is building the connection in probability space and sampling it. In fact, these two things are different. You can build the connection, and then you can sample it separately. Once you realize that, there's many more possibilities that you can, so that's essentially what we did. And so you can do that, it's the same thing. You can, any diffusion or stochastic bridges that involve stochastic process, if you realize that they equal in law into something simpler, you can work at that simpler level. Let me skip that. I don't think. Okay, so there's another thing that in fact is, I think, older than diffusion, and that is called denoiser. Okay. And a denoiser is actually something which is actually simple. Let me try to see. Is that, okay, so if you can think about, I'm going to phrase it again in the context of interpolant to make the connection, but you could think about it in a different way. So think about x of t as being the signal x1 that has been dimmed because you multiply it by this beta t that kind of dim it a little bit, and then you have added noise to it. Okay, that's the z. Right? So it's very easy that you can easily show that the expected value of the expected value of the data given the signal, the noisy signal, is the expression that they've written in the box. It's just an elementary little calculation that again involves this Stein identity is called as a result of Stein unbiased risk estimator. Sure. Okay. So people have been using that quite a lot because that tells you that if you have a noisy image and you know the nature of the noise, you can use this estimator in a way to kind of denoise the image. It's not a generative model in the sense that I explained because this is the base optimal estimator for the data given the signal, but this is not something that gives you sample from row 1. It's just a conditional expectation. But if you want to make the connection, which what I discussed, is that you can actually realize that you can denoise from different levels of noise at any given time. Okay, that's the formula. It's a bit of a mouthful, but it's just expressing one guy into the other. And then you can realize something that, in fact, I think people like Eros Simoncelli, know very well, is that when you do the denoising, instead of denoising in one shot, you should denoise in very tiny little shots. You do infinitesimal steps of denoiser. And in fact, you can justify that because you can show that if you denoise by infinitesimal step, what you get is a generative model. In other words, if you use this denoiser, this formula, and you iterate upon it, what you end up having is just an integrator for the probability flow ODE that I've written for you before. So there's a close connection again between denoising and the framework that I'm presenting here. Okay? Okay, so how am I doing with time? Do I have a little bit more time or? Oh, I forgot. Okay. So, okay. Okay. So I want to switch gear now and do something which is like, because I didn't completely know, I assumed that the audience was interested in physics problems. So these, which I think you are. So what I've been discussing here is in some sense a problem that I know that many people would kill me for that, but it's a simple problem in some sense because it's a problem of sampling where you are given the data. When you do sampling typically in StatMech, it's not like that. You're given a model and you're trying to find, samples through the model. That's much harder because you need to discover where the mode of your distribution are, right? Rather than having given samples. Okay. So I want to go more to, so the method that I've discussed here are also applicable in the context of sampling, as I mentioned at the beginning. It is harder because if you start from no information and you want to do sampling of complex distribution, in general, it's hard because you can't discover the modes. But I want to discuss kind of an intermediate case, which has to do with active matter, okay? And I realize that there's probably many people in the audience that know more about active matter than me, but I'll stick my head out anyway, so I'll discuss a little bit. So active matter, as a system, you are an example of active matter, I think. So there are systems, that are made of simple constituents that interact with the environment, extract work or put work back in, and as a result can do things that are quite remarkable, but they are fundamentally out of equilibrium. So there are examples for, bacteria, bird flock like the one that are there. And I think is the movie playing. This is a movie that's from that was done at NYU by Paul Shakin. These are little colloidal particles that are active swimmer if you put them under light. And so if you remove the light, they are passive and they are just a gas. And then when you put the light in, they start to swim into a certain direction and they make these clusters. Okay. And the question I want to address here is, okay, we know that these systems do many things. And this is related to the fact that they are not in detail balance. They break time reversal symmetry. And so what I would like to try to address a little bit is, can we quantify that a little bit? Which is what, they're out of equilibrium. What does that mean? And are there signature of the non-equilibrium that you can actually calculate? Okay. And I'll connect this to the problem that we have been discussing before of, the score-based modeling. So I'm going to look at one specific problem, which is a system of, these active Austen-Uhlenbeck particles. Okay, so what are these active Austen-Uhlenbeck particles? So it's the first equation. So these are particles that have a repulsive force. So they tend to get away from one another. That's the F in the first equation there. But then they have a persistent force, which is telling them that they stubbornly need to swim into one direction. And this direction is satisfying an independent Austen-Uhlenbeck process for every particle. So it changes, but slowly in time. So there is persistence. So they are stubborn. They just want to swim into one direction. And then if they collide with one another, they keep going at it like, okay. And so what can happen is the blob that you have there, that's a simulation of this system, is that if you adjust the parameter of this system the right way, and this has by now be well studied, they undergo what's called motility-induced phase separation, which is there's a gigantic traffic jam, essentially, that happens in the system, which is that they kind of jam themselves into this big cluster, which if you were to remove the persistence force, right, if you were to make this system take V0 equals 0, so you remove completely the swimming aspect, it would just break apart, like in the actual experiment. This is numerical simulation, but the previous one was an actual simulation. So I'd like to understand this a little bit. Okay. Okay. So to facilitate things, I'm going to just write the full system. So above is a system where the xi, there's n particle, x is 2 dimension, g is 2 dimensions, so it's 4 times n dimension. We're going to run all that into a compact notation, which is R, and write down that as an SDE. And I want to analyze what's going on with that. No, this is periodic boundary condition on the torus. Okay, so they've right. So this cluster slowly move and deforms a little bit and would go, but it's a periodic boundary condition. Okay, so is this I didn't write it explicitly, is the F. F there is like it's a repulsive force, so that is actually it's a soft repulse. It's not like a Lennard-Jones for this simulation, but it's stronger than this. So if you were to zoom on that, there's a kind of a triangular lattice structure.
Is there something there that's very close to the superficial?
Yeah, that exactly. It's a pairwise interaction force. Every particle look at every other, but with a short range interaction, and they are soft sphere. If they got in contact, they bounce away. Okay, and the velocity, the persistence force here is not strong enough so that they could fly, swim through one another. So even though they are not hard sphere, they are soft sphere. They are sufficiently hard to beat the other guy. So that's why they do this cluster, and they don't swim across one another. Okay, so so this is completely standard. I wrote this slide this morning, so if we pause them, I need to adjust them and put a few references. But this has been studied by Mike Cates, Julien Tailleur. There's many people that have looked into that. The references are missing. It's my bad, but I'll add them. Okay. Okay. So now I apologize. This is like a few formulas, and probably you all know them. But just to remind yourself of this, is that if you look at this, so this system, this SDE, which you need to remember, I'm writing it compactly, but the microscopic system is the multi-body problem that we are looking at, right? You can write down a corresponding SDE, a Fokker-Planck equation for it. That's the equation that governs the probability density of the full system. So this, again, is a probability density that takes all the variables. It's like the Schrödinger equation with many electrons. It's like a big thing, okay? And then you can write this equation, and you realize that, again, you can write it, so the right-hand side, right, involve a probability current. That's what I wrote as J. And you can use this guy to define what's called the current velocity by saying you define J to be V times rho, and the V is written in the last equation before the box. Okay? These are just notations so far, right? But the main difference between an equilibrium system and a non-equilibrium system is that a non-equilibrium system, when it reaches statistical steady state, non-equilibrium statistical steady state, its current is non-zero. dt rho is equal to 0. Statistically, nothing moves anymore. But there is a current that persists. That's the signature of non-equilibrium. Okay? At equilibrium, in a Gibbs distribution, if you extend that, then you would have not only dt rho is equal to 0, but J, the current, would be equal to 0. Now, there's a bit of so you can rephrase that by looking, in fact, at the velocity and give a slightly more stringent definition of what is a non-equilibrium state, is to say that's a state for which the divergence of its velocity is equal to 0, is not equal to 0. The reason why you want to do that is because there are systems that otherwise would be non-equilibrium that are equilibrium, like under-damped Langevin equation is an equilibrium system that has a non-zero current, but that satisfy divergence V is equal to 0. So we're going to take this as a definition, okay? And once you have done that, and that's the last slide, you can now start to look at signature of non-equilibrium by actually looking at what you would want to look if you look, there's one object, which is that you can look at the Gibbs entropy minus rho log rho, okay? And then you realize that you can actually, so this guy at statistical steady state doesn't move, right? Because rho is in time independent. But the way it doesn't move is interesting because individually the particle could create entropy and destroy entropy in the system. And so there's a way to quantify that precisely by looking at the divergence of V or V square. Okay? And so that's what we're going to look at. Okay? And the reason why, okay, so why, let me go back one slide. I'm going to try to motivate this a little bit. But you recognize in this formula the grad log rho there. That's the score that is being learned in score-based diffusion. So we have no tricks, tools to learn this. So that's what we're going to use, okay? That's in 2 slides. Bear with me for a second. For the moment, we're just going to, I'm going to try to explain why this is important. Okay, so let's look at one so that you see what are the objects, you know, in the flesh of what we're going to be looking at. So this is a simpler problem of an active particle, which is an active particle in a quartic well. So if it was at equilibrium, because there is a well, you would just get a density which is centered at in the center, right? But there is this persistence force that can either be positive or negative and tends to push it against the wall of the well, okay? And so what you observe if you do that is that if the well is quartic, so if it's sufficiently flat and then sufficiently steep, this induces metastability in the sense that the particles tend to stick to a wall until it reverses velocity and then it sticks to the other wall. And so the trajectory, the panel that says trajectory just show you one specific trajectory in this system where if you look closely, you see that it sticks a little bit in particular here to the wall, but it's a bit of a mess. The picture that says non-equilibrium steady state, so NESS PDF, is the probability density function of this system at equilibrium that you can calculate. As you can see, it is bimodal. The system tends to stick to one of the wall. And when it sticks to the wall, it has the velocity that is associated with going towards that wall. Okay? So even though the velocity field here has something, the velocity doesn't see the position, the persistent force doesn't see the position. The position sees the velocity and induces a correlation between the two. And as a result, you get that when you look at the joint, so if you look at the probability density function in this joint space, X and persistent force, you have this bimodality. It would remain even if you look at position, but so it's the graph that's there, okay? Correspondingly, there is a probability current. That's the one that you see there. So the particle go to a wall and then they stay there for a while, then they go to the other wall and they stay there for a while. And then you can look at the flow line of this probability current. That's the one that is there, which is of course much more rigorous. It tells you, the probability current is evolving in this system. This is not very important, maybe. This is more important, which is that if you now look at the divergence of this current velocity, this is what you see, is that it's completely concentrated at the wall. And even though there is no net entropy production in this system, right, because it's a steady state, you see that what happened is that there's entropy that is produced. So there's transfer of entropy from the particle to the wall when it collides to the wall, and then it's restored when it comes out. And these are these two modes that you see at each wall, right? And so this is a signature in this system of where what is non-equilibrium. Here is what you would expect is the interaction between the wall and the particle, right? That's what creates non-equilibrium. Okay. Now, it's all nice and fine, but I'm not interested in that. We want to scale this to high dimension. And so the idea is that, well, we can take the toolbox that I explained before. So this is a bit of a chart. I don't know, is this the only one that's where neural network? But essentially what we do is that you take data from the particles and then you use them as you would use for images. You know, they are particle data instead of being image data, but that doesn't really matter. And you do that and you learn the score by regression, okay? And when I say you learn the score by regression, I mean this high dimensional function. So it's something which takes the input of the position of all of the particles and all of the G, and gives you a vector of the same dimension, which is the grad of the log of rho. So it's big, but you can, in principle, learn it. And there's a little architecture which is using, you know, we use a transformer where first you embed into a larger space, feed a space, and then you do the learning. I mean, this is the standard thing. Okay. And with that, I'm almost done, because if you do that, you can actually do something which is, again, is pretty remarkable. So we have not, I mean, this is like a recent paper with Nick Buffy. We have not, there's more that can be done, I think, with this, but you can learn the score on these systems that involve all the way to 30,000 particles. In fact, it's transfer learning. You learn for smaller number of particles, not that small, like 4,000, and then you can transfer. And then when you ask, I try to do the same plot as I did before, but of course here, I cannot show you the full state space because that's very high dimensional, but I can show you on every one of the particles how much entropy or work, if you wish, it's doing in the system. And then what you realize is that essentially there is no entropy production in the gas, which is what you would expect. There is little entropy production in the solid, which is also what you would expect, because over there, essentially nothing moves or they are jammed. But all the action is at the wall. Of course, in the previous example, the wall was an artificial wall, whereas here the wall is the wall made by the particles themselves. Okay, and so the top row is just the particles, and the bottom row, you color them by the value of the divergence of their velocity individually, like on every one of the particles, and you detect this entropy production. Okay, and since, again, this is something that you can learn, and once you have learned this, you have the function that allows you to look at entropy production indirect. You don't need to use it on the training data set. This is actually not the training data set. And so I don't know if this movie will show actually, but we can try. Is it in fact playing? Right. So you can actually now take trajectory data and just color it by the entropy production as it moves. So you can look at, you know, where is the, so what you see here is the wall seems to not move, but in fact the particles come in and out of it, and it's just that the ones that are out don't do entropy production, the ones that are in do, and you know there's something like, you also see from time to time things that looks like particles zipping through at very high. This is not that, it's just like when there are defects in the solid, there's entropy production at the edge of the defect because there's something going on. Okay, and so as I said, this is a fairly recent work with Nick Buffy. I think that there are quite a few things that can be done with this, but maybe more importantly, which I think is the message that I want to convey here, is that these methods of machine learning are, of course, very interesting in problems with data that come from data science like image, but they also have potential for old problems where now we can start to do computation that were not feasible, or we thought were not feasible just 10 years ago. Right? Because 10 years ago, you would have said, well, we're going to just look at the non-equilibrium, the non-equilibrium statistical steady-state probability density function of a system with many, many particles. People would have said, okay, how do you want to do that? Like, I mean, you know, it's a high-dimensional function. You will not be able to learn it. But we know that there are instances with image where you can, so we tried here, and that seems to work. So I think it's worthwhile. I think it's a route that is worthwhile investigating more. Okay, and I think I'm finishing a little bit ahead of time, but I think nobody will blame me for that. It was a long day, so thank you for your attention. I can show you. I mean, this will be days like the papers. You know, we can look at them. I zoomed out, but we can look at. Thank you.
Thank you, Eric, for the wonderful talk. Maybe we can see if there are still some questions, also from the chat, if you want to write down questions. So, okay, got it.
I have a question about, so the whole construction kind of relies on its philosophy, which I think is affecting in a continuous way. So what if you had like binary data or just like black and white, not grayscale, black and white? How is this going to
That's hard. That's hard. That's also, I think, a comment that Dima made, which is that you know, in discrete space are difficult to optimize upon or move because they are discrete. So this is really relying on things that are continuous. And in the case of images, that requires doing all kind of bit dirty tricks, which is that you need to clip the data, for example, because the data is actually not really in RD, which is what we assume, but it's, you know, it's whatever you have for the channel of that specific pixel, and so it needs to be capped to this value. And there's all kind of trick, but we treat them. Everything is treated as continuous. Yes. Yes. So if you don't have access to the equation of motion, there are, and again, I apologize for not having the reference, there are recent work by Paul Shakin, Stefano Martiniani, where they use, and Dov Levin, where they use information theoretic definition of entropy, where you actually just can look at snapshots of. So we believe that we can, so we are moving into that direction to try to use these techniques to actually do that as well. If you don't have the equation of motion, however, there will probably be, you know, because the entropy production is ultimately related to the breakup of time reversal symmetry, you need to be able to access at least the velocity, which means that so if you have data of your system, you don't have the equation of motion, but you have data acquisition at a rate which is sufficiently fast that you can calculate velocity field or infer velocity field, I think all these methods are applicable. If, however, you have snapshots which are separated in time by days or whatever, and then I think it's going to be much more tricky. In fact, I believe in that case it's impossible. Because clearly, right, and something that I should have maybe explain a bit better, the probability density itself doesn't contain any information about whether the system is at equilibrium or not, and so does the score. There is no information in the sense that if I give you a probability density, right, you can always write it as a Gibbs density or Gibbs distribution, and you can always write down an equation of motion in detail balance for which the equivalent distribution will be that density. So you need to have information about how things move in the system to quantify the breakup of time reversal symmetry. If you have the equation of motion, that's what we use here. You can use the information about the score, which you would calculate even from snapshots, and you use it in concert with the, you know, the equation of motion, and that gives you what I have here. If you don't have the equation of motion, then you would need to infer something about the dynamics, and if you don't, I don't think it will work. But that's a long answer, but. I don't know. So there's two, okay, I can tell you a few things about this, okay? From a technical standpoint, if you want to control the log likelihood or quantities like that, the SDE is better than the ODE, simply because we have better tool with SDE than with ODE. Like we can use Gersanoff and things like that, whereas ODEs are intrinsically complicated objects. But I don't know whether this is a reflection of a true fact or it's simply a reflection of the fact that the tools that we have to analyze ODE are more, you know, poorer than the one from SDE. Now, in the original paper from Yang Song and Stefano Herman, they made a big point into saying that these are not normalizing flows, which means ODE, they are SDEs. And they even gave some evidence that they were working better as SDE than ODE. But I'm not completely sure that's actually still the case. I feel that they felt maybe a bit that they wanted to distinguish their framework with what existing one. And there have been recent study, for example, by NVDIA, where they use the ODE and the SDE, and I really don't see any significant difference. So there's advantage to both. Like if you want to have maps 1-to-1, then you should really do the ODE. And if you want to calculate likelihood, you also need to have the ODE. If you want to do sampling and have diversity, then you can use the SDE. But I would suggest to do it more, not by using the reverse SDE like in the score-based diffusion. You can actually tune the diffusivity that you want. So you can, if you wish, you can tune that to explore as you put more noise in your SDE, or you're going to get diversity of sample from the one that was produced by the ODE, for example. It's kind of, I mean, so it's a cool gadget. Like we have not explored that, but there is many things like that that could potentially be, exploring more detail. Yeah.